Okay, I guess it's time. Let's get started. Good morning, everyone. I hope you have had your breakfast and you're all set for a session. There are some ground rules. Before we go there, let me just give you an introduction of who are the presenters. We'll be talking about the design and performance of industrial concrete floors now. We will talk about the Indian guidelines, the practices, the do's and don'ts, and the actual work that happens on ground. Right. So I'm Ramesh Maganti. I will be the moderator of this session. I will be joined by my presenters Piyush Sahani from Yugal Floors, Navneet from Bekaert, and Mr. Ramakrishnan from Monofloor. All right. Some ground rules. Okay. All audio, as you would already know, has already been muted so that you can have a seamless experience and a learning time. Okay. Ensure you have a proper bandwidth and you're closer to the connectivity, which is the best in the place that you are in. So as to avoid buffering issues and you can get a seamless connectivity to it. Okay. If you have any concerns, as usual, please drop a message to the chat box. We will try and resolve it at the best. Okay. Keep a bottle of water or a beverage next to you so that it keeps you hydrated. We're going through summers now in India, so it's better that we stay hydrated. Ensure your phone is off or in silent mode so that you don't get disturbed. We will provide some sufficient bio breaks. We understand it's a 3-hour session, so you would need some breaks in between so that you have an effective participation and learning. During the course of the webinar, you'll see a lot of material, and we suggest that you don't keep your doubts to yourself. We suggest that you keep dropping in your questions into the chat box so that we can take note of it and answer them at the end of the webinar. Okay, and we will have 3 dedicated learning sessions. So we would request all of you to keep your families informed so that you don't have any interruptions anywhere. We'll try and stick to 1:30, which is the closing time of this webinar. Okay, so this is what we have for today. We have I will be taking through some of the challenges that we have as we speak and why the need of this webinar itself or a learning on industrial flooring. And what to expect from the webinar is something that I would try to give a little bit of a sneak peek into it. Our first presenter will be Piyush Sahani, who will talk more on earthwork, sub-base, the basic foundation of the entire floor itself, including the materials of construction and the judicious choices that we should do when we choose those materials. Okay, we will try and give you a bio and rehydration break in the middle, followed by Navneet. Navneet will talk purely on the design of floors, the current practices that we are following, where are we on the guidelines, what are the best practices that we have. We have taken some sort of a leap from all of our old practices which are there, which are prevalent around the globe. We will talk about that. We'll talk about the flooring guidelines, which is part of the Indian Concrete Institute committee guideline TC09. We will also take you through a case study so that we are able to put the theory into practice. We will put that across. We will try and give you one more biohydration break, and then we will talk about what are the myths. What do we call it as a perfect floor? Is the glass top a perfect floor or not? Is something that we will talk about. We will talk about free and defined movement, how the flooring design itself is very different for each of them. We will talk about the performance of concrete floors, the quality management part of it, and at the end, we would want to hear from you all your questions, queries, so that we can answer to the best of our abilities. Okay, so taking this forward. Okay, coming to the most pertinent topic of why we have this webinar. Okay, we have a lot of challenges. Industrial flooring has been a thing that has been changing because the industry itself is changing, and it is changing from years and decades that it has changed. The impact of the floor on the floor is equally important. So let us see what are those challenges that we have and try to see if we are able to address many of your concerns or queries that you would have. Also, probably beat some of the age-old practices. Is the way I'm doing is the right way to do it, or is there something that I should do differently? How it will help if I do differently? So let us try and address those questions as we go along during this webinar. Okay. So let us go back a little bit in the past why this industrial flooring became so pertinent. So we had the first industrial revolution in the 18th century in Europe, and at the time Arnold Toynbee coined the word industrial revolution. To the second revolution that we saw much later in the 19th and 20th century, we've seen major advancement in the field of industrial engineering, and all that impact of that industrial revolution has been dealt on the floor, and the floor is one that has endured all this during this various decades of time. So we have gone from mass production to the speed of production to efficient production. Okay, now we are going into a lot of automation as we speak. Okay, the industry has changed in its true sense of the need to outperform each other. So we had our first industrial flooring guideline, which was published in India in 1970, which is ISO 2571. But considering the impact and the variance it has on the regular floor construction, but it has not been updated since then. It has stayed then, and it is probably does not address the rapid changes that we have seen over the last 2 decades in the industrial floor and the flooring construction itself. Right? Do you see something different in this? Is the floors bearing the same? Is the floor enduring the same thing? It is different, right? For different floors, you have different types of flooring. That is the need of the hour. Can we design the same floor for all of them? No, right? So that is what we would like to emphasize more of, how to design the floors specifically for the purpose to fit in. Okay. So we also hear this common terminologies that we say. We have the contractor who comes and says, "Oh, what's a floor load?" And the client says, "Simple, 5 ton per square meter load chal jayega. Don't think too much." Okay. We'll talk about flooring reinforcement, saying 8 mm ka 200 mm center to center both ways kar do, ho jayega. You also hear saying single reinforcement kafi hai yaar. Forklift is not very forklift hi chal raha hai, zyada nahi hai. So, and we also hear some of this terminologies which goes back in time, saying, "I don't have any problem with my existing floor. Why should I do something different now?" Okay, the plastic sheet I've put in there, so I don't think subbase is very critical. You can go ahead. Let's add some water on the surface. Traveling becomes smoother. We'll get better floors, shiny floors. Hardness are a challenge. Why do I need that? Okay, my consultant told me he's done a lots of projects, so design is perfect. Let's follow that. Okay, older floors are better than today's floors. So just follow the same design. Yeah, I don't want to reinvent the whole wheel. A lot more. These are some of the things that we commonly get to hear. But is it true? Is it true in the real sense that we speak about the same floor that is enduring so much more? So some of this, I thought we'll bring in some of the true and the root challenges that we have. Okay, the realities as we speak. So these are some of the sub-base failures. You would see settlement. You'll see slab areas which are cracks happening all over. Okay, we have delaminations, we have reentrant corners, we have parallel cracks, and parallel cracks are something that is pretty commonly seen, and we know why we do it, but we still see that prominently across our floors. Okay, nicely see a socket joint, and you have a crack right next to that. We have a lot of joint failures also. Okay, where it was supposed to be, it does not crack. It is cracked everywhere else. Okay, so what can we do? How we as the civil engineers change this going forward? Let us look at what we intend to do during this webinar. Okay, so here what we want to talk about is, it is the function that defines the form. Okay, so let us design the floor for the functional parameters of it. Is more critical, right? Why various elements of the floor are critical and not just the concrete? Let us put the concrete on the floor and the concrete will take care of everything under it. Does it happen that way? Let us look at that. Why vapor barriers are required? Okay, what are the it has been a big theory in itself. Okay, so let us try to bring some parallels, let some understanding around that. How to know you have a floor that meets your functional requirements? You have built a beautiful floor. Are you sure that it has met your functional requirement or not? Let us try and understand how to measure those expectations. Let us do a reality check. And first and foremost, what to expect out of a floor? Instead of saying I need a floor which will take care of everything under the sun. Is that how it is? Or is it something that we can be more specific on how we want to do it, whether it is for today or whether it is for the future? So are we designing the floor for today? Are we designing the floor for future? How predictable the future is? Let us look into that. Okay. But thankfully, we have a document now under the ICI umbrella, which is called the TC09. Okay. So this is the document that has been published by the Indian Concrete Institute. You would see that it has covered the entire paradigm of the industrial flooring, so which includes the design part of it, what each material does, what are the various options that you have, whether it is going to be reinforced floors, fiber reinforced floors, whether it is steel fibers, plastic fibers, all of that. We talk about a lot on floor maintenance. We have the entire design of joints, what are the surface tolerances that we have, what is the surface protection that we can do, okay, which have the overlays that comes in with that. We have the complete futuristic trends that we have, which we have captured along. What we have done is we have tried to bring in the best of the practices that we have, which is relevant globally. Some of you would be aware of the codes called TR34, which is the prominently heard of code in the industrial flooring. We have tried to take a lot of references from there. We have also looked at what is more practical in India. Now, would that be most relevant code that we talk about in Indian context? So we have tried to make an Indian document now. Okay, so this is something that is there for all of you guys. So I suggest you please have a copy of it, read through it. Probably we would make a small impact in the industrial flooring industry itself. Okay. So my first speaker who's going to come on this would be Piyush. Piyush is the director for Yugal Floors. He has more than 8 years of experience. He's a IIT Madras alumni. Okay, he has delivered a lot of floors, a lot of high performing floors, super flat floors, FM2 floors, and he's advised many clients. And where we see that his experience, we will try to build on his experience today and see how we can take a leaf from his experience and improve our respective project sites or work methods. Okay, his company specializes in industrial and warehouse floorings, flat floor constructions, and they have complete pan India operations. Okay, so I welcome Piyush on the floor here. Let me introduce my other speakers also. My second speaker would be Navneet Narayan, again alumni of IIT Madras. He has over 12 years of experience, and of that, 10 years he spent designing concrete structures. Okay, mostly through steel fibers. The company he represents is Bekaert. He is the technical manager for Bekaert, and he started his career from Los Angeles. He relocated to India and joined Bekaert, and his interest has been into structural design and the performance of floors and designing of floors for various conditions. So he would be the right person to take us through the design of floors, which will be the second speaker for the day. Okay. So going to the last but not the least, Mr. Ramakrishnan, who is the general manager for Monofloors. So he's concrete enthusiast, if I can say that. He's the most prolific speaker and a very enthusiastic person with 12 years of experience in technical and sales and marketing, and various consulting roles. He has played various roles in multiple companies. He started with Ultratech, worked with BASF, Bekaert. Now he's with Monofloors, who's sort of giving you a report card of saying, is your floor right? Have you designed the floor right? Have you executed it right? So he will also be talking about what we should do to be able to achieve the right floor. All right. So this is what I have as part of my front up. So I invite my first speaker now, Mr. Piyush Sahani, to really take over the first part of the presentation.
Good morning, everyone. I'm Piyush from Yugal Floors. Thank you, Mr. Maganti, for the beautiful introduction of all the speakers and setting the right tone for this webinar. I would like to take a moment to introduce Mr. Ramesh Maganti. He's a distinguished person in the industry. He's right now the national manager projects at Hindustan Coca-Cola Beverages Limited. He's been working as a civil engineer for more than 20 years now, and the 10 most recent one of those have been spent as the company's not work just in India but also in SAARC countries. He has about 4 greenfield projects under his belt and more than 50 brownfield projects. Not just that, he's an ace master planner. He recently designed the Hindustan Coca-Cola beverages corporate office in Bengaluru, and he's also been recognized as the minds behind the best workspaces in India. So we're really honored to have you as our moderator, Mr. Maganti. And so I'll just switch over to my presentation now. And as it loads, I just want to tell you it's about earthwork and materials. In materials, we'll be going in fair detail in about concrete. All right, so my presentation is up here. There'll be a bit of a lag within the slide changes, so you'll have to bear with me. All right, so this is how my presentation is structured. The first section is about earthwork. We look at some very basic, simple concepts that every one of you can relate to. I'll help you visualize soil as a spring, and we'll go in some history of highway engineering as well. We look at plate load test in a fair bit of detail. Next up, we'll try to understand subgrade. We will look at some compaction bases and finally end with subbase. In the second section, that is about materials, we'll start by visualizing shrinkage, as that is the fundamental principle that goes behind a lot of design philosophies. We'll quickly look at slip membrane and vapor barrier. We'll spend a fair bit of time understanding concrete, and then we'll finish off with looking at reinforcement. All right, so we'll talk about earthwork now. I just skipped a slide, I think. Go back. Okay, so this is just very basic stuff, definitions of subgrade and subbase. Subgrade essentially is the soil that you fill your building with to bring it to grade. For example, if you're building a warehouse that is about 4 feet from the road level, you would just fill that 4 feet with soil that is usually available at the site itself. It is the cheapest material of all. And once this is done, you lay a layer of subbase. Subbase is essentially a layer that comes between the concrete floor and the soil below. It has 3 basic functions. First of all, it transfers the load from the concrete slab to the soil below. It acts as a filter media for water. It is more applicable in a road scenario, not so much in an industrial floor. And more importantly, most importantly, it holds construction traffic. We tend to underestimate construction traffic. I'll show you some pictures later to make it obvious. And next slide talks about some very basic steps. So we dump the material, we level it using a motor grader or a blade mounted on a tractor, and finally we water it and roll it. And after all this, we test it. Now this might look very simple, but each of these processes has a certain way of doing it. For example, if you don't dump your material right, you end up shifting a lot of material from one end of the site to the other, which is very expensive in terms of cost and time. Next up, so a lot of engineering principles of flooring have actually been derived from highway engineering. And essentially there are 2 kinds of roads. There's this blacktop or a bitumen road and a concrete road that is also known as a rigid pavement. Most of the industrial flooring principles are actually derived from rigid pavement design. And if you notice, I've mentioned CBR and plate load test. A lot of us are familiar with CBR, which is actually derived from flexible design and is not so relevant for rigid pavements. Plate load is what is used for rigid pavements. So that is what should be used more than CBR. I have a slide. We'll talk about that more. Okay, so trying to understand how flexible pavement works. So this guy is sitting on a bunch of mattresses, and the load is progressively transferred to the lower mattress. So the lowest mattress is kind of like your subgrade, and your topmost mattress is like the bitumen layer. So what is important to note here is the pressure decreases as the depth increases. That you might be able to understand in the triangle that I've tried to draw here. So you can use cheaper, lower strength materials in lower layers, and you need stronger materials in top layers. And if you look at the right top, I said weaker the subgrade, thicker should be the sub base. So that is how your sub base is designed, taking into consideration the subgrade. It's taking some time to load the next one. I think I skipped a few slides here. All right, so this is how a rigid pavement works. This is how slab action works actually. So if you notice the cot, the first picture, the ropes, the blue ropes are actually the slabs, and that the load on the slab or the ropes is transferred to the horizontal posts or the beams, which further goes on to the vertical columns, vertical posts, which are the columns. And on the right side, if you see the guy sitting on the cot, the ropes are in tension. That tension is transferred on the frame, and which ultimately is transferred to the column. This is the exact same way how an industrial slab works. That will become clear in the next slide. All right, so and a cot has 4 legs, and in industrial floors, you can imagine it to have infinite number of legs. So nothing changes. Your industrial floors has the same moment, same negative moment, positive moments, your tension, compression as a normal slab has, just to help you visualize this. All right, now we'll try to look at how a spring works and how it is extended to soil theory. So an unloaded spring, if it is loaded with a force F, extends by a distance x. And if you increase the load by 3 times, the displacement also increases by 3 times. Essentially, you can imagine a spring as a rubber band, as an elastic that you can push and pull. And in the mathematical equation, it looks as F is equal to Kx. K is the spring constant. Or if people who are familiar with plate load test, that is the K value that you get in a plate load test. Okay, so now combining all the concepts together, this is how designers assume soil to be. Soil is nothing but a set of springs, and the concrete slab is nothing but an elastic plate that rests on those set of springs. And all this was actually done by a gentleman called Westergaard. And how do we determine how good or bad this spring is? That is done by plate load test. And if you're having, if you want an easy aid to help you visualize all the spring stuff. So the first picture, the mattress in the blue, you can see the kid has actually just submerged in the mattress. That would be something, you can think of it as soft soil, or a soil that has been not very well compacted. It will have a lower K value, like it will get you a lower value in a plate load test. The second picture is like a hard mattress, or you can think of it as soil that has been very well compressed. It will give you a higher K value when you do a plate load test. Okay, so this is how a plate load test look like. So the first picture is what I've been speaking about earlier, trying to visualize the soil or the subgrade as a spring. Second picture is more of a test setup. You have a set of plates. You load a jack on those plates. You have a certain amount of dials to note the movement, the deviation or the displacement in the plates. And the jack is you have reaction load on the jack through a fully loaded truck. And the third picture is an actual site picture where you can see the plate, the jack, and the truck, a fully loaded truck that is giving the reaction. One thing I would like to mention here is ideally we should be using 750 diameter plates, which have been used in various sites in the country. I'm not talking about outside India, I'm talking about India, and they have been used successfully. There is a lot of people tend to use 300 plates, which is not the correct way, even though the code allows for correction for plate sizes, but it is best to avoid and use a 750 dia plate for this test. So this test is as per IS 92141979. You can look at that for more details. All right, so this is how a plate load test chart looks like. On the x-axis is the pressure in tons per square meter. On the y-axis is the settlement. You record the pressure at 1.25 settlement. In this case, it is about 20 tons, and you use these two numbers to derive your K value. I won't get into the calculations here, but that is basically the concept. Okay, so a lot of us are familiar with CBR. So the ICI TC09 code that Mr. Maganti talked about earlier actually gives you a table. So if for some reason you're not able to do a plate load test, you can do a CBR and try to get an equivalent K value. This is actually best avoided. You should do a plate load test because CBR is a material property. It does not evaluate the site compaction, which is very important. But the plate load test does evaluate site compaction because that test is done on site after the compaction has been done. Okay, so now talking about subgrade. A subgrade, or simply put, the soil, it essentially has four components: gravel, sand, silt, and clay. Each soil has some percentage of each of these. Now, gravel and sand are called as coarse materials, and silt and clay are classified as fine materials. It is obvious gravel and sand are coarse, they're bigger in size. Silt and clay are smaller in size. And the most important difference between the two is their behavior underwater. Silt and clay can tend to show expansive behavior. They also lose a lot of strength when they are in a wet condition. So a good soil has to have some of each of these four elements. All right, so again, some factual information from the code. So anything in my presentation that you see in red has been actually taken directly from ICI TC09. That is what the code says. So the code recommends a minimum K value of 40 megapascals per meter, a dry unit weight at least of 1.75 grams per cc for the soil, a liquid limit of less than 35%, and a plasticity index of less than 10%. Now, LL and PI are used to ensure that we are not using too expansive a soil like clay or silt. So now what do we do if the subgrade is not of good quality? There are two things we can do. We can either stabilize the soil using cement or lime. They are known as binders, or we can replace the top 1 or 2 feet of the poor soil with a better material. If the soil is really bad, you might have to go more than 1 or 2 feet. Again, the ones highlighted in red have been our recommendations given by TC09. Okay, so talking about compaction now. The first picture that you see is what I do encounter in several sites where, let's say you typically want to compact about 6 feet. What people do is just dump the soil in 2 layers of about 2 feet, 3 feet each, and they roll just the top layer. Now the problem is, if you're rolling the top layer, it has a bulb of influence that you can see in the picture, the white semicircle. Below that, it does nothing. So you still have loose soil below that red line. And the right way to compact is actually to do it in layers, typically of about 200, 250 You test each layer. You do a proctor test on each layer. You either use a vibratory roller or a static 8 to 10 roller, 8 to 10 ton roller. And then finally, on the final layer, you do a plate load test. The next slide talks about the recommendation given by the code, the guideline, sorry. Okay, so it should be compacted to at least 97% of maximum dry density. Now, maximum dry density is obtained from Proctor density test. If you're using a vibratory roller, your compacted thickness can be up to 250 mm. If you're using a static roller, your compaction thickness should not be more than 200 mm. From 1.5 meters from the walls and obstructions, you need to use a plate vibrator. So now we get into sub base, or the layer that comes between the subgrade and the concrete floor. There are essentially four kinds of broad categories. The first one is what we generically call as a granular sub base, or waterbound macadam, or water mix macadam. Second one is PCC, or plain cement concrete. Third is muram, and fourth is puff panel that we used in cold storages. So muram and puff are special cases. In case of muram, so muram essentially is there is no distinction between subgrade and subbase. Muram is used as a subgrade as well as a subbase. You need to be very careful about the material quality here. The puff panels, it's basically a board that goes between the floor and the soil to act as an insulation. It usually has a lower K value. So what you do is you calculate the K value or test the K value of the board and the soil, and you use the lower of the two. And now we look in a fair bit of detail about GSB and PCC. All right. So how granular should the GSB be? What should be the stone size? How much sand you should have? These are pictures taken from 4 different sites, and I'll let you be the judge here. But the guideline gives uses tables from Morth to help you grade the GSB better. So there are about 6 gradations. You could use any one of these 6 for your sub guidelines that the code gives, the TC09 gives regarding how you should be handling your sub base. It should come up anytime now on the screen. All right, so the maximum stone size should not exceed 50 mm. The GSB should be compacted in layers of 100 mm thickness. You can use a vibro roller or you can use a static roller. Again, the maximum dry density the code specifies should be 98%. Now you should target these levels between 0 and minus 15 mm. It is very important that you do not have any plus points, because any plus points means you're compromising the thickness of the slab above. It should be free from steps, ruts, depressions, voids, and sand should be used only as a closing layer where you have open stones or open voids. It should not be used as a separate layer as some people tend to use. All right. Now talking about PCC and its relevance in flooring. This is a very important slide because a lot of us tend to use PCC a lot. First important point is you can never measure the K value of a soil system where PCC has been used, because essentially PCC gives you an infinite K value if you try to do a test. And it cannot make up for bad compaction. If the soil below the PCC is not compacted well, your sub base or your floor is bound to settle down. PCC is not going to offer you any extra protection against settlement. Most importantly, no cutting or filling is possible once it has been laid. Unlike GSB, as a flooring contractor, when we go to a site, we see that the levels are off. We are able to cut the high spots and fill the low spots if it is GSB, WBM, or WMM. We cannot do that with PCC. And PCC compared to GSB is slower and also a more expensive process. So there are certain limitations when it comes to flooring compared to a granular subbase. All right, so these are some good examples of how a well-done subbase and subgrade looks like. You see construction traffic moving on them, and you can barely see any sort of depressions or marks or any damage on them. You can barely see tire marks. And the next slide would be about when we are actually doing the floor. So you should not underestimate the impact of transit mixers on your sub base. You should keep a roller standby to maintain your sub base, because the concrete, the trucks are heavy, and they, especially in a granular sub base, you need some sort of maintenance. All right, so this was pretty much it about the earthwork, but this is not all. There are other things that we can talk about. There are a lot of other tests like grain size analysis, free swell index. What should be the frequency of testing? Rama will cover this in his presentation and in some detail. We can actually project sub base K value from sub grade K value, and there's and how do you treat puff codes? The code has more detail on this as well. All right, so I'll jump into materials straight away. So before I get into specific materials, I would like to help you visualize shrinkage. A lot of us talk about shrinkage in concrete. It seems like an abstract concept, but just to help you visualize, it is nothing but something like an orange peel. So an orange peel has water, and if you leave it on the table to dry out, it loses water. So that is exactly what happens with the concrete floor also. The concrete floor loses water and it shrinks. And lot of design principles use shrinkage. They try to capture shrinkage a lot because it has a huge bearing on the performance of the floor. And it will become obvious when you hear Navneet talk about design. So this is one concept that I would want to drill into your minds through my presentation. When you think about industrial floors, the first thing that you should think about is shrinkage. And I hope this orange helps you remember that. It's taking some time. All right. So we talked about the earthwork. Now, between the earthwork and the concrete floor, we put a layer of something called as a slip membrane or a vapor barrier. These two are different things. I'll talk about slip membrane first. Again, the guideline says the slip membrane should be an LDPE sheet, 200 to 300 microns thick. It should be smooth because essentially what it is meant to do is reduce friction between the sub base and the floor. Because as we just discussed that the concrete shrinks, and because of that shrinkage, the slab moves. And this slip membrane allows the slab to move without cracking. This reduces the shrinkage stress in the concrete and lowers the possibility of cracks. Now, so this is an important point here. If you double the layer, if you put two layers, you're able to reduce the friction by half. So this is something to ponder about for designers. The marginal cost of two layers is very low. So if you're able to reduce your risk by half, should you not be specifying two layers instead of one layer? Something to think about. Now, second is the vapor barrier. It is actually an HDPE sheet and not an LDPE sheet, typically 200 microns thick, having a permeance of less than 0.2 to 0.3 metric perms. So it does everything that a slip membrane does. In addition to it, it minimizes the transfer of water from ground to floor. Now, where is it important? It is important where you have high water table scenarios. It is important where you're doing some sort of a coating on the floor, because if floor coating can fail, you can have discoloration, you can have fungal growth. I think next up should be concrete. All right, so before we get into concrete for flooring, I would like to spend some time just explaining you the process of flooring. So the first picture is the guys are placing the concrete. Second picture is they're using a leveling equipment. There are several. What I have shown you here is a laser screed. Third picture is spreading or broadcasting hardener in initial stages of finishing. Fourth picture is closing the surface. And finally, the biggest is the nice glossy finished floor that comes as an end result of all these sub operations. So next slide would be, as a flooring contractor, what sort of parameters are important for me. There are a lot of things I can talk about. This is a big subject, but just to keep it very high level and simple, essentially three things we are looking for: workability, finishability, and usage of the floor. So when I talk about workability, so all those guys were technical in the group. The concrete should be moderately cohesive, as excess cohesion makes placing, compacting, and finishing difficult. In layman language, what trying to say is we need a certain amount of slump to be able to handle the concrete properly. We need some amount of bleed water to prevent plastic shrinkage cracks, because that water layer on top of the concrete slab helps prevent this. Now, once you've placed the concrete and talk about finishing, we definitely want to avoid excessive bleeding, but we do need limited bleeding water because hardener needs some water to be able to bond with the base slab and also to prevent delamination. Further, as final step of finishing, we need sufficient fines and paste content to completely close the surface while traveling. I'll go back to the pictures again, and I hope these points will become obvious when we take a relook. Finally, as a user of floor, you want to have minimal shrinkage and curling in the slab. And as a floor constructor, I can ensure that by limiting my cement content and limiting my sand fines, because higher cement and higher fines in the sand will result in higher shrinkage and curling and consequently cracking. Okay, so what as a concrete designer, now what can you do in your mixed design? That is what the next slide will talk about. And there are also certain points that the guideline gives us to help us design the concrete.
Is Piyush audible?
Hello, can you hear me? Guys, can you hear me?
Yeah,
Yeah, we
Piyush.
can.
Yes, yes. Go ahead, Piyush. Go ahead.
Yeah, okay. So I think slide is taking a bit of time to load. Yeah, okay, I think I missed one. Sorry, guys, you just have to bear with me on this one.
Yes, the slide is loaded, Piyush. You can continue.
We can see the slide.
So, so
Yes.
you can see the mixed design slide. All right. Okay, I can. Okay, so the first
Yes.
point is the slump requirement varies from contractor to contractor. There is no one slump that you can define for a flooring contractor, even though it is not unusual for the slump to be between 120 to 170 mm. I'll show you a picture to make it clear. So the important point for you to know here is that the slump is controlled by varying the admixture dosage and not water. A lot of people tend to think that higher slump means higher water. No, it is not the case. Secondly, the water cement ratio should be in the range of 0.47 to 0.55. This is what the guidelines tell us. This is what I agree as a flooring contractor. I'm actually very happy to see this point in the guideline, because concrete does need water. There is, in the next slide, I'll talk about evaporation. We need water to prevent plastic shrinkage. We need water for the hardener to bond properly. And a lot of people panic when they see, when I ask people for a 0.5 water cement ratio. Okay, what can we do to control shrinkage? Avoid needlessly high cement. A ballpark range would be between 325 to 375 kgs per cubic meter. Use zone 2 sand because it has a balanced amount of fines. Also, test your silt content because it leads to higher shrinkage, and more importantly, it increases the risk of delamination. The stones should be well graded, and when you're using fly ash or GGBS, be very careful because it can lead to dusting if not handled properly. The densities are different, the mixing times are higher. So I hope it is amply clear that floor mix is different from a standard general purpose mix design. And in my next slide, I will talk about evaporation. And while the slide loads, I'll just keep talking about it. So we never, as designers, we never take into account evaporation. We need to realize that the moment the truck leaves from the RMC plant, the concrete starts losing water. And once we have placed the concrete, or we have put the concrete on the in the panel, it sits there for about 3 to 4 hours losing water. So, and once we start the finishing, well, the slide is just, so once we start the finishing process, we need even more water for the hardener to be able to bond to the slab. So what I'm trying to say is, if and you can use these 4 parameters and the graph on the right: air temperature, relative humidity, concrete temperature, and wind velocity, to actually calculate the rate of evaporation of water from concrete. And you can do this exercise and you'll be amazed at the amount of evaporation that is happening. As in essentially, all this increases the risk of delamination and a compromised surface. We do not want a compromised surface. I've already loaded my next slide. I think it's suddenly become slow. I don't know why. So next slide, basically, in the next few slides, I'll basically be reviewing the pictures that I showed you earlier. I want to emphasize that when we talk about slump, uh, uh, so I talk about slump because slump is a requirement of the men who are handling the concrete as well as the machine. Uh, because when we are doing large panels, right, we typically do about 600, 700 square meters a day, and we handle one truck every 15 minutes. So if you have like a 90 or 100 slump, the guys would not be able to, to pull the concrete and place it. So they need a certain amount of slump to be able to handle it. And machines like so each machine has a certain requirement. Like okay, the slide is here. We use a lot of laser screed. So the laser screed also needs a certain amount of slump to be able to work properly. I've loaded the second slide while still talk about this one. Okay, so if you can see, right, it's a big panel, and you need it's a fast process. You need to keep pouring, you need to keep leveling. So if you get a tight load, the guys just get stuck here. So so this is why slump is important. And again, we are not adding water to increase the slump. We are just adding admixtures. This is something that I do face a lot of resistance as trying to get this point across to clients, to RMC plants, that this is what we need. So in while the second slide loads, the second slide, I talk about a bit about finishing in hardener. I have a picture there that shows how the hardener is actually wetted. When you spread it on the floor, you will see 2 shades of hardener. One is light gray. Okay, sorry. Okay, I jumped this slide. So a lot of people get uneasy when they see this picture because they see a layer of water on the slab. Now, this is not actually a bad thing because this bleed water is preventing plastic shrinkage cracking. If the evaporation is happening at too fast a pace, you will see cracking that I've shown in the picture on the right, the plastic shrinkage cracks. You might have seen these in your floors. So this is one. There are several ways you could add glass fibers to control plastic shrinkage. But certainly having some amount of bleed water helps keep your slabs safe. I've loaded the next slide, and that is what I was talking about, hardener. So in that you will see two colors of the hardener. The light one is where the hardener has been broadcast on the floor, but it is dry. The dark one where it has been wetted, it is just to help you, drill the importance of hardener, wetting the hardener. It's not really slow. Okay, so here the picture's up here now. So if you notice, the guys are using a hardener trolley to broadcast the hardener. It is, if you can see the trolley, it is dry. And on the floor, you can see two shades of the hardener if you look at it closely. The light is where it has not been wetted. The dark is where it has already been wetted. So this is what I'm trying to stress, that we need water to be able to wet the hardener. And if this is not taken care of, you can have delamination. That is the picture on your right. You see about a 2 to 3 mm uh, layer on the top coming off. All right, so this is the finishing slide. So if you look at the first picture, you need a certain amount of paste for the guys to be able to finish and give you a nice glossy floor. So we do need a certain amount of cement, certain amount of fines, but we need it in a balanced manner. Too much of it is not good. Too less of it is not good. So you might have realized uh, through this presentation that there is a lot of push and pull happening as far as concrete design is concerned. We just need the right amount of water, cement, fines for this whole thing to work properly. Guys, just bear with me. I just have about 7 more slides to go. We have the reinforcement section after this, and concrete is almost done. I'm sure you will not have this issue with other presenters because they have a slightly different system than mine. Just bear with me for another 5-10 minutes, and we should be good.
Your slides are visible. Piyush, you should go on.
Okay,
No
fine.
problem.
All right. Okay. So this is my final slide on concrete. So guys, again to stress that flooring concrete is different. See, when you're building a column or a beam, you do a lot of form work. You spend a lot of time forming, and when it comes to concrete, you pour it and you just leave it there for a day or two and then deform. That is not what happens in floors. As you've seen in pictures, there's a lot of processes happening. We're placing, we're finishing, just dealing with concrete on a very active basis. So this is how uh, our trade is different. So our concrete should be different from general purpose concrete is what I'm trying to stress here. All right. So the next section is about reinforcement. So while the slides load, all right. So these are some more. I can just keep on going about concrete, but I have to do justice to the time. So we can talk about concrete rheology, admixtures, cold joints. How do we maintain consistency? How do we take care of abrasion resistance? There's something called as a finishing window in terms of time that we need to be able to finish. Uh, okay, so why do we need reinforcement in the first place? So we need to realize that concrete is a brittle material, and grade slab can actually be designed without reinforcement, but it will have serious limitations. It will be costlier because the section is going to be thicker. The mode of failure would be brittle, and that is not the case when you're using reinforcement. The shrinkage behavior is unpredictable. It is more sensitive to any quality issues that might have because reinforcement acts as an insurance. And in terms of reinforcement, there are broadly two categories. You can have reinforcement bars or well mesh, or you could have fibers. Fibers are either synthetic or steel. All right, just talking very briefly about steel bars or well mesh. The guidelines specify a minimum grade of Fe415. Now, what is important to consider is the position. This is a very common question, should your mesh be at the top, the center, or the bottom? It is important to know that if you're placing at the bottom, you're doing it to increase the bending moment capacity of the slab. If you're doing it at the top, you're doing it to manage the shrinkage better. And if you're putting it at the center, it does nothing, because center means you're at the neutral axis. It's a technical point. Lapping, cover, and spacing are the key details to take care of. And unreinforcement section still stays vulnerable, because this is not a 3D reinforcement like steel fiber. Okay, weld mesh. The weld mesh is nothing but steel bars that have been welded together. The significant difference between weld mesh and steel bars is that you need a lesser amount of lap if you're using a weld mesh. They are available in different sizes and diameters. The next slide would talk about steel fibers.
Piyush, it's loaded. The slide is already loaded.
Steel fibers.
Yeah.
All right. Okay.
Yeah.
So essentially, there are two kinds of steel. There are two kinds of
Fibers.
fibers. One is the steel fiber, and the other is synthetic fiber. There are wide types of fibers available in terms of their sizes, shapes, properties. What is important to remember is that it should have a high tensile strength. It should have proper anchorage in the concrete mix. When I say anchorage, I mean it should be able to bridge two aggregates. And most important, your steel fiber or your synthetic fiber should have a higher modulus of elasticity than hardened concrete. If this is not the case, it's not going to do anything sitting there. And the biggest advantage of steel fiber is that it is dispersed in a three-dimensional manner in the concrete, so it takes care of your top, center, bottom, and helps in better stress distribution. So this is my last slide, guys, more factual. So essentially, the important point take from this slide is that there are two types of synthetic fibers, macro and micro. Micro synthetic fibers only help in controlling plastic shrinkage. They are not structural. Second point is you can get steel fibers as loose or glued. You can get macro synthetic fibers as loose or pucks. Now the Young's modulus, if you notice, steel fibers give you about 200 to 210 GPa, but macro synthetic fibers give you about 3 to 10 GPa. So I think I'm done here. I would not waste more time loading my thank you slide or the. I'll just. There's one summary slide. Let me just. Okay, so the slide is here. So this is a summary of what I tried to talk to you guys today. Plate load test is more reliable than CBR test. You should put stress at site on doing layer by layer formation of the subgrade and not just dump material in one go. BCC should be reconsidered, because it is only as good as the compaction below. As flooring contractors, we need high slump. For ensuring workable, needed to take care of delamination, and we also need to consider evaporation of water. Thank you, guys. I'll hand it back to Mr. Maganti. Thank you for your patience and time.
Thanks, Piyush. It was a fantastic presentation. Okay, I'm sure a lot of you guys have taken a leaf about the practicalities of doing things. While we have been hearing it for age-old days, saying that this is how it is to be done, I think it is about trying to bridge that practicality to theory. So it is good presentation by Piyush right now. I'm overwhelmed by the number of questions that have come in. I have more than 100 plus questions. That makes it that much more appealing for all of us, because that means it shows your interaction, it shows your participation in the program. Thank you very much. We are very glad to see this. Okay, while we'll try and answer some of the questions, I'm sure 100 questions is a little too much for Piyush also to be able to answer in a short period of time. We will try and squeeze it. I mean, no doubt we would want to address some of the things. That is the reason for this webinar. We will definitely work this up. The clock in my system reads 11:28. So what we would do is we will probably take about a 5-minute bio break. You want to rehydrate yourself, pick up a cup of coffee, tea, whichever region you are in. And then connect back at 11:33. So we will be starting the session sharp at 11:33. So I guess for now, you can take a break and then you can join us back. All right. Thank you very much. So 11:33 it is.
Rama, if you're saying something, we cannot hear you because I guess you're
Muted.
muted.
I was muted. I'm sorry. I was muted. Yeah.
Okay.
We hear some complaints about few complaints of some people talking about network quality. Please make sure you log out and log in again if you face some issue. Make sure you have a stable network. Because when Piyush was talking, the rest of the three sitting in three different cities are able to hear him seamlessly, which means his network was okay. So just try to reconnect from a stable network. Maybe that should solve the issue. Thank you. Thank you very much.
Ramesh, Piyush, and Rama, if any of you are typing, can you just mute the mic so that it doesn't show up?
Yeah.
Yeah, thank you.
Sure. Sure. Yeah. Thank you. Navneet, you can maybe post your first slide. You're due to start in next 2 minutes.
So, Rama, am I loaded?
Perfectly.
Yes. Yes. Very clear. Very clear.
Okay.
And
So,
I guess you wait for 1 more minute so that Ramesh will kick you off, and then kickstart your presentation, and then you can go.
of course.
Uh, maybe Mr. Ramesh has taken a break. I think you should start. We are already on time.
Okay.
Perfect. I'm here.
Yeah,
I'm
Ramesh
here.
Ramesh is back. Okay.
I'm here. I'm here. All right. Okay. So we get started, gentlemen. It's time 11:33. I'm sure you guys took a little bit of a break after sort of an enlightening session by Piyush to enlighten us about the do's and don'ts at the site. Let us get a little more deep diving into the concrete floor design itself. This is going to be a heavy session, so guys, buckle yourself up. Navneet is going to take you through this session. And let us try to clear all our qualms, all our concerns about the right design of floors and why it is different from designing any other thing. How floors design is different from others. Okay, over to you, Navneet. All yours.
Okay, thanks, Ramesh. Uh, this session of the webinar will be covering structural design and detailing of industrial floors. And basically, in the agenda, I'll be walking you through the need for structural design of an industrial floor. What are the current practices which are being followed in design offices? Some of the international guidelines which are available and their relevance in India, and then the new guideline that Ramesh and Piyush were referring to, ICI TC09. How relevant is that for us in India? And I'll be also covering a design case study as per ICI TC09. Now, the question is structural design needed for an industrial floor is is if you just ask anybody in the industry, you can a lot of times get these kind of qualitative responses. For example, people could come up to you and say, okay, I have very minimal load, is can I just provide 75 or 100 pcc? My sub base is very much compact and it is rock solid, so do I need any reinforcement? My entire floor will be under UDL and it will deform uniformly, so there is no bending. Why is a floor design needed? And for example, this is a very typical one, the last one. I have used the same design in all my factories for several years without any problems. Please give me the same proposal. So I'm sure a lot of you would have faced these kind of questions from clients, customers, or even yourselves must be thinking on these lines. But the problem with all these responses is they're only qualitative and they're sort of based on assumptions. And you don't really know what's the performance required, and they're not quantitative. So, for example, if I say minimal load or a compact rock solid sub base, what are the numbers behind which justify those assumptions? So that's a gray area. So in short, yes, you do need structural design for industrial floor. And if you look at the current practices that are being followed in design offices, essentially what you see is the first one, a lot basically follow the client requirements, which is based on the client's experience and budget. And also typical grade slab details from old projects are followed, for example. Also, it's possible that we are seeing this more and more these days, where the design responsibility itself is offloaded to flooring vendors or applicators, so to speak. Some design offices have design spreadsheets, so some of the old ones do the design based on IRC 58, which is a highway rigid pavement design method. And there are some new Excel sheets that are available based on ACI 360 and TR34, which are some of the international guidelines which are popular for grade slab design. Of course, you also see the use of FEM design tools like STAD or SAFE, etc. And it is also a fact that we do not have an IS code for slab design. So if you look at IS 456, that is relevant only for structural RCC members and not grade slabs per se. And of course, you can calculate the section capacity based on IS 456, but it doesn't give you a complete picture of the grade slab design process. So what have we resorted to as a country? So we have international guidelines and the relevance in India. If you look at that, what are the international guidelines that we have? So some of the most popular ones are TR34. Both third and fourth editions are used. And you have ACI 360, which is also popular, which is American guideline. Now, mind you, these are very good guidelines and they offer great insight into the process of structural design of a grade slab. And especially in the absence of an IS code, these are very good tools for design. Now, the only problem is we have to really understand if we are applying right engineering logic and applying these judiciously in our environment while arriving at the final results. Now, for example, it is a fact that these guidelines do fail to capture the inherent variability in the material properties, the level of construction quality, and the local environment conditions that we have in our country. So this is a challenge. Um, for example, typical project like this on a grade slab, where is the rebar cover? Uh, where is a slip membrane? Do I have a slip membrane? And the concrete itself doesn't seem too good. It looks very harsh. So these are the real scenarios that we have faced in our sites. And how do these guidelines address these issues in a way in terms of reliability of the design itself? Um, and if you look at the fundamental differences do exist in design philosophies vis-a-vis our traditional methods of design. So, for example, it is common knowledge, and most of the consultants do talk in these lines that if you have minimum shrinkage reinforcement, it could be 0.12 to 0.15% of reinforcement. It is normally needs to be provided on the top of the slab, and the main reinforcement is at the bottom, because on the top that is where most of the shrinkage and temperature effects are faced, and that's where the cracking is seen. And this is completely different, let's say for example in TR34, which normally provides only a single layer of reinforcement, which is very minimal, sometimes quite less than 0.15%. It's about a 6 mm or a 7 mm rod, that's it, and that too at the bottom of the slab. And how does this go with this typical Indian situation that we have, where the reinforcements get deformed because of moving trucks, or the chairs get deformed, so the reinforcement doesn't actually stay in place. So this is an issue. And as I mentioned, Piyush has covered PCC in great detail as a leveling course for sub base. Now, if you have a nominal mesh at the bottom on such a stiff layer, do you think it's going to provide sufficient bending capacity? Now, that's also a bit of a question, if you ask me. And sometimes it so happens, funnily enough, that as a compromise to both of these views, the steel mesh is right provided in the middle. For example, so top is preferred by our guys here, and we say no. Okay, TR34 says bottom mesh. Can I put something in the middle as a compromise? The only problem is this mesh is neither good enough to hold the shrinkage cracks tight, nor is it good enough to basically help in bending. So it goes down as a waste anyhow. So these are some questions that we need to ask as designers ourselves. And also a fact that we must bring it out is all most of these guidelines are based on characteristic cylinder strength of concrete. So for example, ACI is purely based on cylinder strength. TR34 is based on Eurocode 2, which also has cube strength, but the notation is always given like this, C25/30 or C30/37. It's a cylinder/cube strength notation. So, for example, C3037 means an M37 concrete. Now, how do you make an M37 concrete in Indian context? All these questions. So, and also this has an importance of the properties itself, which I'll talk about later in the next slide. But minimum grades, for example, TR34 gives you such a table where the starting itself is from M30, which may not necessarily be the case in a lot of our sites actually, because of the availability of materials and so on. So, or the design need itself. So this is a question that again we need to ask. And also depending upon which code you're going for. So if it's ACI or TR34, the Young's modulus, which is by the way an important parameter for the grade slab design, the Young's modulus of concrete, that also quite varies. For example, ACI gives you about 24 gigapascals for an M30 concrete, whereas TR34 gives you about 31 gigapascals for an M30 concrete. Whereas IS 456 gives you a equation 5000 root FCK, that's about 27 gigapascals more or less. So it's somewhere in the middle. But you can see there's a variable. This variation also causes something like 5 to 10% of variation in the design results itself. So this is something that one must ponder over. And also, this is something that has been observed over the years. Most of these guidelines completely ignore the corner load condition, and there's no load transfer ratio or equation provided for corner loads. And we see quite often that this is one of the main reasons of cracking on floors at corners, more so when you have an early edge loading where you have completely these factors missing. um, and also, please note that these are not sometimes gold standards. They are all of course published abroad. They have been well researched. They are very good, but there are some inconsistencies in these guidelines also. For example, again mentioning about TR34, um, it says that okay, you can consider a load as a center load if it is merely a distance L away from the edge of the slab. Now, what is this L? Now, this L is nothing but what we call, these designers call as radius of relative stiffness. There is a formula, fancy formula. This is also given in our guideline, by the way, ICI TC09. And to tell you physically what this is, it is nothing but it's a point of contraflexure, or where the curvature of the slab changes. That is what is a measure of radius of relative stiffness from the point of application of load. Now, actually, if you go by the original theory of these guidelines based on Meyerhoff or whatever, they tell you that the central load condition is when it is about 3 times the elastic length from the edge. Whereas, for example, TR34 somehow bypasses that and it says, okay, if it's L plus the load radius, that I can consider as my central load condition. Now, mind you, this has a great importance on the design because, by the way, this L value for a typical, let's say for Indian projects, it is about 600 to 700 millimeters. Now, what that means is that, let's say if you have a point load which is only half a meter or 600 away from the edge of the slab, of a jointed slab, by the way, or even a free edge condition, you can start calling it as a central load. Now, intuitively, you should realize half a meter is not so much, or 600 is not so much. You can, in no way, you can qualify that as an central load condition. It has to be at least 1.5 to 2 meters inside, away from the edge of the slab. So these are issues that we also need. I mean, over the course of time, we have realized that there are inconsistencies in these guidelines which also need to be addressed, and we can't just lap them up just as it is, as such. Now, then coming on ICI TC09 and the applicability of that guideline in the Indian context for design, I would say uh, in this presentation, I would be covering mainly 3 chapters: chapter 6, 7, and 8. Chapter 6 talks about loads, chapter 7 talks about the design process itself, and chapter 8 is about joints and details. Now, if you look at loads as such, uh, what is this one thing that we are obsessed as a country? Um, what is that one thing you're obsessed about? Uh, okay, this is the joke, but of course, average kitna deti hai? You may have a super bike, and then people want to ask ki mileage kitna hai? How much is the mileage? You may have a fantastic, most costliest vehicle, but people want to know how much is the efficiency, fuel efficiency. Something similar is seen for flooring also. So, how much UDL will my floor take? This is very common point that people ask. Now, this has unfortunately been ingrained in our mindset, and this is across spectrum: contractors, consultants, clients, everybody uses this quite often. And unfortunately, we must realize that this is a sort of a fictitious load case, because the concept of UDL is coming mainly from old industrial floor design, and the mindset that the machine load must be divided by the plant footprint of the machine, and simply whatever you get is the design load. This is not, of course, the right way, because the real loads are almost always applied by way of point loads on the grade slab, or line loads if you have a wall and so on. But that's how it is. And of course, you need to go through detailed machine layouts or cantilevering equipment, material handling equipment, data sheets, racking layouts to be able to find the right design load for the floor. We can all decide from henceforth maybe to say, okay, at least start talking about point loads and fix a common base plate size of, let's say, 150 by 150 and say, okay, how much point load capacity does my floor have? At least that would be a welcome change from what we have been doing for all these years. So in TC09, the guideline is very clear. It talks about point loads. It talks about what should be the intensity of the load, the contact area, the distance between the loads, and so on. And it tells you how you need to account for those loads in your equations while you are putting those in your formulae. Same thing, wheel loads are also defined. So you could have a forklift movement or a truck movement happening somewhere on your floor. So the intensity of the load, the distance between the wheels, the tire pressure, all of that becomes an interesting parameter for design, and that is needed as an input. In stationary loads, we could have line loads and UDL. Yes, you could have those also. So, for example, typically line loads are in this form. You could have an infill wall resting directly on the slab, which would exert a line load, or you could have, let's say, some rolls like this, which are stacked one on top of the other, and then that would also impart a line load. And then you could have UDLs. Of course, UDLs are possible, but then only in this condition where you actually are looking at some stack of bulk material like this. And just I would like to point it out to you. Just try to recall in your projects and try to remember, if at all you really had a UDL like this in your floor. So if you and that would tell you how or where we are placed actually in with regards to UDL and how we take this as input in our flows. Now, the guideline also gives partial safety factors for various load conditions. So you have the static load 1.2, dynamic load 1.2 or 1.5, depending upon normal traffic or heavy traffic. Impact loads, also you need to have some safety factor included for that. You have material safety factors for concrete, fiber reinforced concrete, and reinforcing steel. And if you are, for example, for loads, if you want to arrive at a global safety factor, you simply multiply individual safety factors like static and dynamic to arrive at the overall load safety factor. Now, design for flexure. Now, it's a technical term. What is flexure? So flexure is nothing but bending, and grade slabs, although supported by soil springs, they do bend. So it is, and Piyush has explained that a bit in his presentation. But essentially, please don't think that you have a very good sub base, so there will not be any bending. There is going to be some bending, and this there will be stresses, and there will be consequent cracking if you don't account for those stresses. Now, typically, you are placing the slab on a set of springs which has a notional spring constant or K value. And the design methods, this is all given the guideline. The design methods, whether elastic or inelastic, are based on the nature of concrete section and reinforcements used. So you could have unreinforced plain concrete or concrete which is having minimum reinforcement, or a single layer of reinforcement or mesh, or you could have double layer reinforcement or reinforcement with fibers. And in the way this is structured is depending upon the concrete section that you have and depending upon the possibility of load redistribution. The methods are either elastic or inelastic, depending upon how the section behaves, whether it is ductile or brittle. Now, for example, what is elastic design? It is nothing. Basically, it is you have this kind of a bending moment diagram. If you have a point load, and what happens is if I apply a load a bit further, you have no further capacity in the slab because the limit has been reached. The flexural strength of concrete is reached, and you cannot go beyond the flexural strength of concrete. There is no sufficient load redistribution possible beyond that. So that's the peak load, and that is what you design for if you have an elastic design, that bending moment. And you have elastic design formulae given as per, let's say, Westergaard's theory for interior edge and corner load. And these are all given as equations. I am not going to explain those equations, but those are given in page, you can refer page 25 of ICI TC09 to get these equations. Now, uniformly distributed load is also an elastic loading condition. And here, please mind you that you can have different patches of UDL being applied on the floor, causing critical moments. So, for example, the first image, you can see certain patch weight causes maximum bending at the bottom of the slab. So that becomes a critical bending moment at the bottom. And the negative bending moment on top is because of two blocks of UDL which are pushing against the soil. and hence consequently there is a bending on the top of the slab. So these equations are also given in page 25 of ICI TC09 as such. Now coming on inelastic design. So for example, now if I have a sufficiently ductile section in my concrete and I'm allowing for load redistribution, what happens is my bending moment diagram shift changes, and I still have further moment carrying capacity, uh, and I can go on increasing the load further until I am able to utilize underutilized sections of the slab. So the moment diagram actually starts shifting up until you start reaching the flexural strength of concrete on the top of the slab. So that is how you end up getting multiple cracking and load redundancy due to highly indeterminate system like this, where you have the slab resting on so many springs. So that is how, depending, because of the nature of the structural system and because of the ductility of this concrete section, you are able to apply this design method. Now, just as we have Westergaard theory for elastic design, we have the possibility of inelastic design being done using majorly two major theories are available, one by Lossberg and one by Meyerhoff. So ICI TC09 refers to Meyerhoff theory to be able, because it's a similar theory and can be easily applied in a design office. So that is what has been referred to in the guideline. So in the inelastic design theory, you could have internal load condition and edge load conditions. So all these formulas are also covered in the guideline. You could have multiple load points, dual loads, or even four times those loads. Those equations are given in page 27 and 28 of ICITC09. Now coming on the capacity itself, so you get a positive bending moment at the bottom and a negative bending moment on the top, and those capacities are given here. So if you are using a reinforcement, the positive bending moment is a function of the area of steel that is provided at the bottom, and the negative bending moment is a function of the area of steel provided at the top, which is equivalent to the cracking strength of concrete. Now, coming on fiber reinforced concrete, what you see is that the positive bending moment is defined by, you can see a parameter there, Fe3K, which is nothing but defined as equivalent flexural strength of fiber reinforced concrete. It's a material parameter that comes by testing of fiber reinforced concrete. And the negative moment on top is based on the flexural strength of concrete, which is the ultimate limit state for the first crack appearing on top. Now, these equations are also given in page 29 and 30 of the guideline. Uh, Mind you, the parameter of Fe3K, there is another guideline, ICI TC01.1, where which provides a basis to calculate the Fe3 value. So how do you do that? Basically, you simply have a 4-point test being applied to a beam like this, IS 516, a typical standard beam, and you plot a load deflection graph. And what you see is that, let's say for plain concrete, you get a brittle failure, you get a spike, and there's a brittle failure suddenly. And this would be typically the plain concrete behavior. Now, what happens is, if I go on, if I use a fiber reinforced concrete, I get a different pattern. I get something like this, where I have now an increase in the load deflection graph. There is a post peak response, and this is typical graph, let's say for fiber reinforced concrete. And this test is done up to 3 mm deflection of the beam. So the 3 mm is, mind you, it gives an indication to you that it's a highly ductile system, and this curve shifts up or down depending upon the dosage of fiber. So if it's very low, it would be actually slanting down a bit. If it's high, you would get almost like an elastoplastic behavior. So that is how you do it. And then typically in the terminology, there is a term defined, RE3, which is nothing but the ratio of the equivalent flexural strength up to 3 mm deflection of the beam divided by the flexural strength of concrete, which is a peak. So the average of this graph up to 3 mm divided by the peak value, which is the flexural strength of concrete, gives you what is known as the RE3 value. You may have heard of this term quite a lot, those of you who are dealing with fiber reinforced concrete. So this is how you actually evaluate RE3 value. Now, the guideline also provides for thermal stresses to be accounted for. So the thermal gradient across the depth of the slab you need to take that moment off from the negative moment capacity, and all these equations for internal edge load and corner load condition are given. You can refer to page 30 of the guideline, and you can find these equations there. Coming on shrinkage, it is something similar approach like temperature curling. You again take off the component from shrinkage also from the negative moment capacity, and basically these equations are given in page 31 of the guideline. Please note that these equations are valid only when you have a plastic sheet. So if you don't have a plastic sheet, the shrinkage stresses are going to go up quite high. So that is the reason why you need to have a plastic sheet here. Now, coming on design for punching. So what do you mean by punching shear? Of course, in layman terms, this is just a representation of that. You punch through, make a hole in a slab because of this kind of a loading condition, and that essentially is punching. But of course, you don't have such a bad situation as is depicted in the image for grade slabs. But nevertheless, it needs to be checked, because sometimes for very thin slabs, it could be possible that it is governing in design, but normally it doesn't. So you do have equations being given for punching shear, depending upon, let's say, if you have fibers, no fibers, all of that is accounted for. And you can refer to page 31 of the guideline to account for those values. Serviceability limit state check. So how do you find the deflection due to a point load? So for an internal load, edge load, or corner load condition, those equations are also provided in the guideline, and you can refer to page 31 for that. Now coming on joints and details. So how do you design for joints, or how do you design for the joint load transfer? Basically, you have a lot of possibilities of joints. Let's say if you look at socket joints. Normally, the socket joints or sawn joints, the load transfer happens by aggregate interlock. Now, what is aggregate interlock? So, if I have, let's say, a load being applied on one end of the slab across the socket joint, you have all these aggregates bridging that crack and transferring some, load across that. So, this is considered as 15% of the edge load at the joint in the guideline, in the ICI TC09 guideline. So, for example, if I have a joint edge plan as shown here, I would have a point load and a load transfer of 15% across that joint if it's a socket joint. The same thing, let's say if I have a corner joint, corner load at a joint, it is considered to be 40%. So you could have a corner load joint corner plan like this, where the load is being transmitted to the three adjoining slabs which are joined to the parent slab. Of course, you could use higher values if you have specific load transfer studies available, depending upon the parameters, the grade of concrete, all of that. But this is what is nominally provided in the ICITC 09 guideline. Also, then the possibility of load transfer in a construction joint when you have dowels. So in a dowel joint, you could have round dowels. You have the capacity for shear, for bending and bearing of because of the action of the dowels, and whatever is the least value becomes a critical value and is used for the design. So that becomes a load transfer capacity of the dowel. Similarly, for now you've seen a lot of these plate dowels are being used in the industry. So the guideline also provides for the shear capacity, bending capacity, and bursting capacity of a plate dowel. So you could also have a pop out because of bursting of these plate dowels, because you have a higher planar area. So that possibility is also given. So the guideline covers those equations quite nicely, and you can look it up and design your plate dowel system also. Now coming on joint layout and spacing. Uh, Basically, if you look at these are in some ways part of the detailing practices. So it is common to locate a contraction joint or a control joint, also known as a socket joint, along the column lines. But usually additional joints are needed because the column spacings could be quite high. So you need to plan for those. It's quite possible that you could have joints in the middle of the column line, which is fine. And joints must be placed in such a way that you are able to have the slabs which are as square as possible. But if you cannot do that, but at least make sure that the length to width ratio is not more than 1.5 is to 1. Now, in the absence of any detailed design, it is recommended by this guideline to have the socket joints placed between 20 to 30 times the slab thickness, and it is limited to 6 meters in both directions. So that's what the guideline talks about. And in terms of detailing, I would just like to ask a rhetorical question here: is it necessary? Is it something that we can escape? Because a lot of these problems that we face actually in the industry, we see that they are a result of lack of detailing. So just to touch upon some points, I mean, if you see some of these images here on the slide, you can see some sort of cracking emanating from a corner of an equipment foundation. You see in the second image, it is a crack in the middle of the panel. So the first one is because you don't have any restraining reinforcement at that location, which could prevent the cracking. The second one is because you went too long on the panel. It is not as square as possible, so it should have been 1:1.5 ratio. The third one is you see two lines going parallel. It is because you have actually a grade beam underneath, which was not sufficiently detailed and not sufficiently isolated, and this led to some sort of reflective cracking on top, because you are actually having a very rigid support there. And the fourth one, even though you have, let's say, a round section and you would not expect any stress concentrations, still you see these kind of cracks coming out of these elements. So the answer is yes, you do need detailing, and a lot of times that determines the success of a project. So, for example, a lot of these detailing uh, practices are given in the guidelines. So, usage of plastic sheet or LDP sheet is imperative to reduce the friction between the subbase and the grade slab. Uh, the second image of restraining reinforcement, or what is known as auxiliary reinforcement. Also notice some isolation around the column pedestal that has been provided, because you don't want to have the structural superstructure interaction going to your grade slab, because grade slab has to be designed for completely different loads. It cannot take the structural loads coming from columns and walls. And also you could have a detail where you could have a circular detail like that, so you are preventing stress concentrations, but also you are having sockets at corner columns, so that they any cracking emanating from there is routed through that socket. Also some sort of diamond detailing, which is quite common in the fourth image. The fifth image is that of a trench. You could have cracking coming from there, so it's quite possible you could have a groove joint provided that way. And saw cutting operation itself, for example, typically the guideline talks about 1/4 to 1/3 the floor depth for the saw cutting operation. But not only that, the timing of socket also, because if you don't cut the groove in time, which is typically less than 24 hours, or at least in that window, then you lose control of the joint. What is a joint? A socket joint. A socket joint is nothing but a planned crack. So if you don't provide a joint there or a weakening there, the slab is going to find its own zone and crack itself into pieces. So that's the reason why you need to provide these joints. And it's a very common practice in Indian scenario. People give something like 10 groove and then leave it. No, you need to go deep enough, because a 10 groove over a 200 thick slab is not likely to going to be the weakest zone. You want these cracks to happen in those locations, and for that you need to make the slabs weaken, and that is possible only when you cut it at least 25 to 30% the depth of the slab. Now, all these other detailing drawings are given in the guidelines, so you have the possibility of corner columns being reinforced with auxiliary reinforcement like that. Interior columns in the third image, you can see all four sides are closely encased with some auxiliary reinforcement. And slab isolation is essential, so you need to have some sort of an isolation pad to prevent interaction between the wall and the slab. And also for internal columns, as I mentioned, you need to have an isolation around those columns. Now, finally, coming on a design case study as per ICITC 09. So we will maybe look at a warehouse project. In this case, you have, let's say, a G plus 6 racking configuration, and each pallet is 1 ton load, and you have two pallets per level. And that, when you do the calculation, you come up with something like 7 tons of point load on one leg. Now, the base plate size is typically 150 by 150 mm. There is a forklift moving, but that's only 3 tons of wheel load, so that's really not going to be critical. You can already start putting your designer's hat, because 70 kilonewtons is obviously much more than 30 kilonewton. The sub-base value has been given to be 0.08 Newton per millimeter cube, which has been achieved on a 750 base dia plate load test. So this is given as an input. And if you design using the rebar mesh, these are some of the design parameters. So let's say the slab thickness of 185 qualifies this design. The cover to reinforcement is 35 that has been provided at the bottom. So that is 150 thick depth. M30 concrete is provided, which has a 3.83 flexural strength as per IS 456. 8 at 300 is provided at the bottom, and 8 at 190 is provided on the top. Please don't get bothered by these weird numbers. I just wanted to arrive at the exact solution, and that's the reason why those numbers have been chosen. And then the E value, the Poisson's ratio, K value, all of that are already, I talked about those. And floor panel dimensions are 5 by 5 meters. Now, when you get into calculation, then you need to calculate the first parameter, which is the radius of relative stiffness, or the L value that I mentioned. I told you this value is about 600 to 700 and that's what you get here. It's about 658 and then the factored load. So 1.2 times 70 kilonewton is 84 kilonewton, and so on. So all those values are given here for interior, edge, and corner. And then you calculate the positive and negative bending moment capacity, find out the capacities, and then you find that it's the corner load that seems to be the critical condition, because at the bottom you see 50 tons of corner load capacity, and you have a 50 tons of load. So it's just matching right at the limit, actually. Now, also the second case could be you could have two loads which are close by, and in that case, then the edge load becomes more critical, because here at the edge you get something like 160 kilonewton against 142 being applied. So again, light, sort of at the limit. You do have a breathing space, but at the limit. The same thing when you apply using steel fibers, we have the same parameters being looked into. And then for here, we are taking something like 15 kgs per cubic meter of fiber dosage of a particular fiber type, and which is imparting an RE3 value of 50% or zero point 0.5, that's the ratio, and all other parameters remain the same. And when you go through the same steps, you again get the same corner load capacity, because here the capacity is defined by the first crack of concrete. So you are not relying on the fibers here as such in the corner condition. Coming on the second load, also the edge load is about 160 kilonewtons, which is similar to what we got in the previous case with the rebars. And when you compare the two solutions of rebars or fibers, you get something like 7.6 kgs per square meter for steel rebars, and you get something like 2.78 kgs per square meter for steel reinforcement, so fiber reinforcement. So you get a lower design dose of steel, dosage of steel when you're using steel fibers, because you have a higher distribution of fibers. It's a three-dimensional reinforcement, and the design methodology is also supporting that. So you get M30 concrete with a 185 thickness. Now that so we are over with that, but in summary, what did we actually cover in this section of the webinar? So limitations of international guidelines for Indian conditions, some of the features of ICITC 09, how would you account the loads properly, the process of structural design itself, importance of detailing, and finally we had a project case study that we looked into. And other key things that you should remember, please get out of this mindset of UDL. That would really help us a lot, help us design efficiently and design the right way. Also insist on a full spectrum of load of soil studies, because you heard Piyush talk about liquid limit, plasticity index, plate load test. um, these are some of these things we find missing in our soil reports, honestly. And rather than just basing our reports on CBR value or SBC, which is not the right parameter, mind you, for grade slab design. So for foundations and for other things, it may be fine SBC, but not for grade slabs. And the design is only half the battle won without proper detailing and site support. All of this is meaningless. So, so you heard about the sub-base materials from Piyush. You heard me talking about structural reinforcement and detailing. So we'll now connect all these dots and bring up the aspect of floor surface regularity, floor performance, and quality control. And I'll now hand over the stage to Ramesh to take it forward.
Thanks, Navneet. Thank you so much for the presentation. I hope I'm heard. Is my audio are you able to hear me?
Yes,
Yes,
yes, we are
yes,
able to
yes.
hear you. Yes.
Perfect.
Crystal
Perfect. All
clear.
right.
Yeah.
Ramesh,
All right.
Ramesh, we can hear you.
Okay. Thank you, Navneet. Thank you, Piyush. So it's been quite a session. Okay, I'm sure we have taken a lot of inputs from there, and I've got hordes of questions. Also, shows that Navneet's job makes it a bit more difficult to be able to answer and relate to so much more of them.
Okay.
We will try to compile those questions and try to come back with suitable answers. One of the common questions that I've been seeing on the chat box is: are we going to have this material available? Yes, we have decided on certain means of how we can make this material available to you, so that people who had glitches in between can also come back and seamlessly run through it. Okay, so this is for the benefit of all. Intent here is to ensure that we impart that knowledge that is there and try to bring everybody on the same page, so as an industry we grow better. So that is the whole intent behind this webinar also. um, Currently it is 12:15 right on the dot, so we will take about 5 more minutes of a break. So what we will do is we will connect back. Oh, it has become 12:16 already. Okay, so we will connect back at exactly 12:30, so that we can try and conclude this session by 1:30. So I understand we are getting slightly into your lunch schedule, but we will try and be there at 1:30. So let's meet back again at 12:30. So take your bio breaks, hydrate yourself back, and then we connect back again. Thank you.
So it's a 13 minute break, huh?
It's 30-minute break.
No. Okay.
Yeah.
Yes, Mr. Shankar, we are on a break and we'll join back at 12:30 sharp.
So I will leave my camera and mic on so that we know that the session is live.
Yes, yes. We'll wait for a couple of more minutes and then we can start.
It's a short break. We're just getting started in a couple of minutes, please. Thank you for bearing with us. Mr. Vinod Iyer, yes, it's a break time. We are starting back in a couple of minutes, sir.
So, Navneet, some more questions coming your way.
Okay.
It has been an interesting mix of questions. So shows that people are thinking varied, having varied thoughts. Couple more minutes, Rama. We will get started.
Yeah, sure. We have not yet started. We're just starting in a couple of minutes. Thank you for your patience.
Okay, I guess we can get started now. We are slightly a few minutes ahead, but I guess more or less everybody has come back, and we can have the session started. Rama, are you set?
Yeah, I'm all set, so I can go right away.
Perfect.
So,
Okay, over to you, Rama.
yeah, okay. Thank you, Ramesh, and thank you, Navneet and Piyush. You have set the stage for me to go on and talk about the further two details that I was supposed to talk about. Now, this is just to clear the agenda that I'm going to place in front of you. First, let's talk about surface regularity. Let's clear some basic concepts of surface regularity. Then let's talk about international guidelines, different documents, what they talk about, and then also touch upon our ICI document, how it compares against the others. I've chosen 4 important performance parameters. You can go on to have many more, but I've chosen 4: structural performance, performance of joints, floor surface performance, and aesthetic performance. So that in that section we will be talking about performance of concrete floors, and then going on to conclude my presentation with quality management, how to do that, and what documents talk about and all that. Yeah. So let's get started with the slide. When it comes to floor surface tolerances, it is all about material movement. If you don't have any material movement in your facility, if you're building a warehouse or an industrial floor and you don't expect any material movement to happen at all, any aesthetically okay floor should do. You don't need anything special in terms of surface regularity. This is the basic of surface regularity. Historically we have been shifting from how we store the materials in our facilities. We started with basic heaps of storage, then we went on to palletize the materials into pallets, and then we went on to storing these pallets in racks. Now we are also moving towards a lot of automation in these facilities. So the evolution of the storage method to store our material in these facilities and to move these materials around our facilities have given rise to the surface regularity requirements that we have. It is not the same that it used to be, it's evolving. So I just want to take this opportunity to clear some myths when it comes to surface regularity or flatness, as we commonly know this. There are some myths. Someone says, okay, I need a 0-0 floor. A client or a user of the building calls in a contractor and wants him to build a super flat floor or a 0-0 floor or a floor that looks like a glass top. There are 2 answers to this question. One, you can never build something like this. The second, which is more pertinent, is you don't even need them. You need only as much surface tolerance that you need for your material movement. So when it comes to flat floors, everybody starts talking about FM2. Previously, it used to be VDF, which used to be a very common way that we refer to floors. Now we start referring to common floors as FM2. Where does it come from? And let's clarify the myths about it. The reality is you don't need FM2 or you don't need super flat everywhere. Let's talk about how to choose and all that going forward. But choice of surface regularity, the fundamental is you will need to decide on what surface regularity you need based on the purpose or the usage. Now, as I already said, material movement, when you move the materials around in your facility, how you move the materials dictates what surface regularity to choose. Usage of, say, any equipment, say a laser screed, is always advantageous, but you should remember that it doesn't guarantee a certain surface regularity. It is important to follow these technologies with good skill and care. So that's very important to achieve what we want. And it is always costing more money. When you actually build it and you want to change the surface regularity, it costs much more money. This is something that you need to remember. Have you seen this in your floors? The reality is many of our floors immediately after we build and we start curing look like this. And some people come back to us and talk about, okay, there are puddles of water, which means there is a level difference that's built in when constructing this floor. And some people even go on to say, when I put a 5 rupee coin, it's fully immersed in water. So there are definitely dips in the concrete and there are level differences in the concrete. So is it acceptable? Some people also categorically refer to this as unacceptable. The reality is, even though it is looking like there are dips in the floor, which in fact it is. There are dips in the floor. There are ups and downs, which is bound to be in a part of the floor construction. The reality is, this particular floor where the image has been chosen has been tested and certified for an FM2 special. We'll talk about a little bit of detail of what that means. It has been certified as an FM2 special floor. So it doesn't. So these myths, like how it looks like when you pour water there, doesn't really relate to the fact to whether it is acceptable or unacceptable. So this is very important to note. Now, when I said material movement, just to clarify one important concept, to clear one important concept, this is called static lean. Previously, we used to have racks which are very short. Used to have racks of 3-6 meters to start with. When the racks started growing taller, when the racks are taller, the equipments that handle the pallets on the top draw from these racks tend to lean if the floors are not level enough for them to operate. So when the height of the rack started increasing, and width of the rail also eventually started to come down, this leads to static lean. So when you have taller and taller racks, the same surface regularity is not good enough because it tends to lean and it may cause a safety or an efficiency issue in the warehouse. So now moving on, to clear two important terminologies when it comes to flow surface regularity: flatness and levelness. We keep hearing this all the time. You can remember it in a simple way. Flatness is something that is measured as an elevation difference between 2 points which are very close to each other. Say something like 100 millimeters or 300 millimeters, depending on what guideline you're using. So flatness is related to points close to each other, right? Levelness is the opposite. It's level differences between points which are farther away from each other. Say, for example, 2 meters, 4 meters, 3 meters, some things like that. So let's just dive more into an analogy which will simplify this even more. This is just to give you an idea of what the difference between flatness and levelness is. A floor that is flat and it is not level is the second one. Is very good on spaces that are close by, but it has a slope, and farther away there is a level difference between 2 points. So this is just to give you a clarity. What is the difference between flatness and levelness, right? In a working environment, you need both. We need to understand that you cannot compromise one for the other. Let's talk about what the implications are going further. What do you need? It is imperative to understand material movement, and you need to understand that a floor that is specified for a certain working is not completely suitable for another type of working. And repurposing or changing the application or changing the usage will mean that you will need to spend something to correct the floor before you can use it for a new application. And then speculative flows, a Tier 34, which is a popular guideline internationally, says if you are building speculatively, you are not completely sure about what the usage is going to be, then you can use something called an FM2, which is kind of an average, neither here nor there, and it's an average, so you can lean on it. Remember, it is always cheaper, easier, and faster to build a floor for a specific surface regularity that you need instead of building it for one and trying to correct it later, right? Now, just to give you clarity, this is what graph illustration I wanted to show of how a material handling equipment in a free movement. So there are two concepts, two ways materials can move in a facility. It can move in an aisle through a free movement where the material handling equipment can move in any direction along the aisle. This is called a free movement. So it can move across the length of the aisle, and it can move across the width of the aisle, and it can move around anywhere randomly. So this is called a free movement. Then going on to the second type of it, which is the defined movement. So here the material handling equipments have to necessarily move along the direction of the aisle, and it can never move across the length of the aisle. It has to move exactly on the same wheel path time and time again through the usage of the floor. It's a very specific kind of a floor. It is also very common that these racks are very, very high. This happens particularly when you have to store a lot of material in a very limited space. The equipments that are used in construction have also evolved over time. We used to have a traditional beam screed, which used to be used for about 4 meters of panel width. Now the methods of construction have also improved. We started to move to a truss screed first, and then we also have laser screed. It is very important for us to take advantage of the better technologies that are available. So technologies like laser screed are very good. They help us in achieving much bigger panels. So this is very important to take use of these technologies. But the fact remains that even when we are using such a technology as laser screed, the surface regularity is not guaranteed. So we need to be careful about what surface regularity we need and what we are achieving, and to make sure we set the process right to achieve that. So an equipment or a technology cannot guarantee you that you have a certain surface regularity by using that equipment. Yeah. So just to give a gist of different international guidelines that are going around, that are talking about the surface regularity. The important ones are TR34, of course, ASTM 1155, and the other one, that is the ICI TC9, which is the Indian Concrete Guidelines document that we have published recently. The equipment used for measurements are, of course, the optical level and the inclinometers, which is the profilographs. Just to give you a snapshot of what TR34 talks about, the word FM2 that's commonly heard by many of us comes from here. So TR34 says, depending on height of racks, you need certain tolerance in both flatness and levelness. So again, TR34 classified flatness as distance between consecutive 300 millimeter points, and levelness as the difference in level between 3 meters. So 300 and 3 meters are the two blocks, or the two data points that TR34 specifies, and the difference, of course, between different categories of these floors are given here in the table. We will not talk too much on the details, but it is important to note that for flatness and levelness, two sets of measurements have to be taken. The levelness measurements have to be taken by optical equipment. It is not enough to have just one set of measurements. It is important to have both sets of measurements. If you have to classify a floor as an FM2, say for example, you should have two sets of readings, which is flatness and levelness, and if conforms to both these parameters, then you can classify a floor as an FM2, say for example. Yeah. So moving on, ASTM is a slightly different approach. The collection method of data is similar. The equipment that can be used are similar, but there are a few differences in strategies. The more important thing is it doesn't now talk about the absolute level differences and just calculates the difference and report. There is an empirical number that is calculated using this formulae, and these empirical numbers are what is reported. So FFFL is the way you denote these surface regularity tolerances when you talk about an ASTM method. It looks like a 45/40 or something like that to classify a floor as based on ASTM 1155. Moving on to talk about how ICI document talks about surface regularity. So now the important part of this is coming from VDMA specifications. So the VDMA is a German association, which is an association of equipment manufacturers. So it comes in from that. So the important parameters that are captured in the document are coming in from VDMA guidelines. So this is what it looks like. So basically, the data points are not just 2, but 5 in this case, and the difference in level between points through different spacing that we identify or measure are 5 in number in this particular guideline. If you look at it, this the smaller spacing, which is a 0.1 meters, indicates flatness, and the ones that are slightly higher than that, which is about 4 meters, indicates levelness, and the other one, the extreme one, indicates more to do with the datum. So you need to have a consistent level throughout the floor area instead of having it in very limited places. It is very important to sample the areas correctly to be able to get a representative level quality. And then, just to give you a picture of how to choose the one particular surface regularity tolerance, say for example an R1, which is for free movement traffic or a random traffic condition, is meant to be used when the height of racks are more than 13 meters. So it's very important to note now the height of racks is being directly related to what surface regularity you need. And say, for example, R2 is for between 8 to 13 meters and R3 for about less than 8 meters. So it's very important for us to know what is the height of the building or height of the racks before we decide a specific type of surface regularity that we are specifying for the floor. Yeah. Now, just to give you a snapshot of the comparison between different guidelines, the ICI TC9 has more data points, 0.1, 1 meter, 4 meters, 10 meters, and 15 meters. Even though you measure using a profilograph of 300 millimeters, you can interpolate then to get the other data points. And then the TR34 has 2. So there is a very distinct difference between how these two documents deal with the surface regularity, and it's pretty much covered until the point that we discussed here. Now, going on to define movement and how it's specified, recapturing how material moves in a defined movement floor, you always have the material handling equipment going only upward and downward. There is no way of lateral movement in these aisles. So there is only one unidirectional movement of the material handling equipment. So almost all international guidelines that are talking about defined movement are very similar to each other in terms of how they classify the floors or how they specify what surface regularity needs to be achieved. So just to give you a gist, the level difference between the left and the right wheel path is captured. The other element that's captured is, of course, depending on the length of your material handling equipment, what is the difference between the different data points along the length of the aisle. So these two are captured, and there are calculations depending on the wheel track and also the size of the equipment. So you classify the floor either as D1, D2, or D3, depending on all of these parameters. The important things to note in this particular type of floor is that in a defined movement floor, only aisles matter. You don't have to worry about the remaining part of the floor. So if you have a 10,000 square meter floor and you have a defined movement area in about only 1,000 square meter, you will, even in that 1,000 square meter, you will have to worry about achieving those level tolerances for these equipment to work only in the aisles in that 1,000 square meter area. So it's the rest of the area can be designed as per a free movement specification, and all international standards are very similar. And it is also important to note, if you have a floor that is meant for defined movement, it is very, very specific. You have to choose your equipment that you're going to run here before even starting to build a floor, because it's much more accurate that way, and the equipments will not work. If you have built for a speculative kind of a floor, then your equipment that you purchase afterwards may not work in the certain scenario. So it's very important to be very specific when we are designing a surface regularity specification when it comes to a defined movement. Yeah. So moving on, these are the equipments that are used. The first one is, of course, the auto level, which is fitted with a parallel plate micrometer so that you get the accuracy that you desire to a least count of 0.1 millimeters. It is very important to record values to the least count of 0.1 millimeters. And the first equipment with auto level and the parallel plate micrometer is necessary to capture levelness. You can't have a swap between one of these, or you cannot choose to use only one of these. You have to have the first set of equipment you need for levelness. The second one is a profilograph, a manual profilograph. So this is also electronic, but the recording is more manual. So this is used to capture flatness. And the third one is a robotic type of a profilograph, which is also used, but it's not very popular in our country. We don't have many of these equipments in our country. So moving on, the correct time to measure a surface regularity is within 30 days after construction of the floor. This is necessitated by most of the international guidelines because that's the time when a flooring contractor moves out of the site, and you can deal with the liability related issues by that time. So that's how it works. Now moving on to the second section of our discussion, performance of concrete floors. Like I already preempted, there are 4 aspects of performance that we will be talking about in this section. The first one is, of course, the structural performance. Navneet and Piyush were very elaborate in covering different aspects of how we capture structural elements when it comes to design of floors. I would like to re-emphasize the importance of it and how we do it. I will not get into details of method of how to do it because they have already done it very well. So it is important in most of the projects. What happens is you have a subbase that is built by a general contractor, and a flooring contractor comes in after the subbase is built. So if you have to be clear in the transition between transition, particularly in terms of liability, between the time when a general contractor hands over the subbase to a flooring contractor, it is important to do testing at that time. So the testing happens in the subbase, and there is a sign off in responsibility. So the flooring contractor is able to take on the responsibility from there on. So the identification of loads is very important. You need to identify, you need to validate also that you are building this floor to a certain structural capability, and you can't switch later. So if you have built the floor for a very low warehouse, you can't then say, okay, I'm going to increase the height of the building and I'm going to house a much taller warehouse, because the loads are different. So it's important to identify the loads and to make sure that you are building sufficiently. And it is important to have a speculative design when you don't have data. The first thing is, of course, you need to design. There is no discussion about whether we need to design. Navneet has dug deep into why you should design, and I will not discuss on this further. But the reality is, you have to design a floor to be specific to your usage. And everybody uses the floor differently. Everybody is different in the way they have their subbase. The materials that are available at each site may be different. So it's very important to design the floor to your specific usage. And if you don't have, in some cases, you don't have the loads that you are going to expect. So some details, like shown in the picture, like the clear height of the building, can give you a fair indication of what is the maximum height of racks that you may be expecting in the floor. So you can speculatively design using the maximum height of racks that you are expecting in your building, so that you will have a floor of a sufficient structural performance. And the design factors also need to be kept in mind when designing. So it is important to design. It is important to review the design. So even if the flooring contractor is given a design and build form of a construction contract, then it needs to be also established whether the design is sufficient. So a design review is also very important, and documentation for all these parameters that we've been talking about, so that we know if we have a problem, we can go back and trace. So documentation is the only way to trace back to the root cause. Touch wood, if you have a failure, is the only way, if you have a documentation, to get back and check how what you've designed for and what loads you expected when designing the floor, and what was the subbase before construction of the floor started, and all of this. Now let's move on to the second performance parameter, which is the joint performance. Now, like Navneet was talking about, the design and detailing is the key. Now when it comes to detailing, you need to detail each of the type of joints differently. Say isolation joints, for example, any alien element in a floor, say a wall, a column, like Navneet was mentioning, load from a column is not designed to be taken by the floor, say for example. So these are elements that have to be isolated. So you have to completely demarcate such alien elements. It can be trenches, it can be foundations, it can be columns, walls, anything. So they have to be isolated from the floor. To prevent, one is a load interference. Second, to prevent the shrinkage, restraints in shrinkage. Yeah. So moving on to the second type of joints, which is the construction joints. You can't build a whole, if you have a 10,000 square meter factory or a warehouse, you can't build everything in the same day. Construction joints are necessary because you have to give day breaks, which are logical. So the construction joints have to make sure they ensure load transfer between one panel and the other panel. The panel that's constructed today and the panel that's going to be constructed tomorrow. There has to be a load transfer mechanism that is inbuilt. There has to be a restraint-free opening. Whatever you do, concrete that is cast on 2 different days don't stick to each other. They will open up. So these joints have to have a restraint-free opening. So this is very important aspect to provide. And edge protection. if you go back and look at any of your floors that you have, the old floors in particular, the one element that has started to fail is, of course, the joints, the edges of the joints. So if you want to protect these edges, then there are ways to protect these edges. Examples are armored joints. So when it comes to control or contraction joints, Navneet was talking about this in detail. This is drawn. This is a screenshot of a picture from the ICITC 9. The depth and the timing of the contraction joint has to be ensured so that the performance of these joints are good. So now moving on to the surface abrasion performance. So the next aspect, we have a stable floor. We have a floor that is good in terms of load transfer and the joint performance. Now the next thing that we need to ensure is we have a surface that is performing well, because this is an extremely important functional parameter when it comes to floor, and the floor can be classified in terms of the load that the floor receives from the point of view of abrasion. You are taking care of the load that is a point load or a UDL that's for the structural stability. Now you have things moving on the floor. So you need to have abrasion resistance in the floor that can take care of these loads. So now, depending on how bad the movement is or how aggressive these movements are, starting from, you can have a basic material movement which is by rubber or pneumatic tires, to going on to very hard nylon, to very hard crawler kind of wheels. So when you choose abrasion resistance, it is important to choose higher abrasion resistance values for more and more aggressive kind of material movements that you have. Say, for example, in a facility like for a earth moving equipment manufacturer who have crawler wheel mounted equipments moving inside the factory premises, then you will have to choose a very high abrasion resistance class. The abrasion resistance class shown in the table, a kind of 0.5, which is the most abrasion resistance according to this document. That's the level of performance from abrasion resistance that you need to choose if you have more and more aggressive. And if you have just pneumatic wheels with very less traffic, you can choose something like even as low as AR4. So just to give you an idea of how it's specified. Moving on, then now we are moving on to a world when all of us are trying to densify or polish concrete to a certain level. So we are moving towards just a rough concrete finish to a smooth, to a polished, to a honed kind of a concrete surface finish. So when we are densifying or polishing concrete, it is important to measure or specify the performance in terms of distinctness of the image. So when we say, okay, we need a floor that looks like a mirror, we have a very highly polished surface, and when you look at the reflection of something, it is as close as possible to a mirror. So that's a class level 4 for you. And depending on how you need your floor to look like, you can have a class 4, 3, 2, 1. This is derived from Concrete Polishing Council from the US, and this is how you can specify performance of concrete when it comes to the aesthetic appearance or the densification or quality of polishing. There are other properties also that are important: the slip resistance, the roughness, and abrasion resistance. All of these properties have some loose connection with the DOI or the gloss, if you want to call it in simple terms. If you want to relate it to gloss, these are very loosely connected, but you can't say that a very high gloss floor will have very poor abrasion resistance or very poor slip resistance. You cannot infer something like that. So it is very important to specify different parameters when we need a combination of these parameters. So they are loosely connected, but they are not directly connected. Yeah. So going on to the last section of this presentation, as an introduction to quality management during construction of your floor. So now, when we have to define quality, the quality is defined as a product or a service that first meets specifications. We need to have a specification, and the quality, good quality, means that it meets the specifications. Then it has to meet the requirements. We may have captured some elements in specifications, but there are something that's beyond that, which are requirements from the actual usage. The third one is, of course, it has to meet the customer expectation as well. There are some elements which are not directly requirements, say for example, aesthetics. These are related to customers' expectations more than just specifications or requirements. So now let's talk about two different approaches of how we can manage quality. The first and the most basic type of quality management is product control. When you have a certain parameter that you want to capture or a certain specification that you want to measure, you execute your project and you go back and test it. The only disadvantage of doing that is you will only be able to say whether you've met the specification or you've not met the specification. There is no way to control how you are able to do this. Things like sub-base check. After sub-base has completely been built, if you go back and test using a plate load test, just test k-value, you can only assess that the result, whether it's okay as per your initial assumption or it's not okay. Things like concrete slump, cube strengths, flatness survey, all these are aspects that are very important to measure and to check if we have met the specifications, but it's also important to control the process, which is the second type of quality management system, which is the process control. Instead of going back at the end of everything to check if we have done it right, the better way to do it is you check the process and you set up the process in a way that you ensure while doing it, you're doing it correctly. So it may be something like a design review, it can be something like a development of quality plan and an actual approval process for different aspects, say starting from raw materials for concrete to batching plant approval to all these aspects. Instead of just checking the quality of concrete by just testing the cubes, can we test the rest of the materials so that we make sure that the process of making concrete is right, so we get the desired results. We are more likely to get desired results and we can eliminate or manage risks much better when we do the process management way. Just to give you an example, Piyush was talking in detail about sub-base and how we test sub-base. And at the end of it, when we are using a sub-base quality parameter called a k-value that's coming out from a plate load test that we are using for the design. Now we talk about the plate load test and a frequency that is given in the ICITC 9, page number 7. So now going back to what this test gives us is just a result. Instead of just testing plate load, testing using a plate load test, what if we are able to test the other parameters? Say the quality of the sub-base film material itself and the quality of how well we are compacting each layer. So if we are testing the other parameters during the process of building the sub-base itself, then we are more likely to end up with the final quality of the sub-base that is being built up that is according to our expectation of k-value, right? So this is the right way. Instead of just testing the result, testing through the entire process, so that we set up a process in the system, so we are able to correct it then and there. Say for example, we specify 98% proctor density for each layer before proceeding to next layer. So instead of finding out after we finish everything that our k-value is not according to our initial assumptions in design, what if we are able to establish on the day that we are filling itself that we are able to get we get a 98% proctor density and we move on to the next level. So we're more likely to have the desired end result than when we are testing just at the end. So this is just to give you an example of how we can use a process control in comparison to a product control, right? So ICITC 9 also gives very good construction checklists. All of you should take a look at this and should use it. Different aspects like a sub-base, site conditions, how well the side shutter is provided so that there is no interference from wind, how well are the top sheets made so that you don't have interference from rains. So if you capture all of this in your construction checklist, and when you are deciding to pour on a certain day, can we have a checklist so that we make sure the load transfer mechanism is installed properly, the levels are checked before we start to construct, the pour plan is in place, the concrete is ordered to the desired quantity, and all of these elements that go into the process of actual construction of floors can be captured using these construction checklists, so that you have a documentation of proper process throughout the entire life cycle of construction of floor. So you capture every single detail. This also goes on to further talk about elements like curing, elements like QC and documentation, or different aspects like testing frequencies, and all of this is covered, right? So that was about quality management. Then I will just summarize what all we have spoken about. Floor tolerance. When we started this presentation, we dug deep into floor surface tolerance, which is very commonly referred to as flatness around in the flooring industry. But the two aspects, that is flatness and levelness, have to be looked at in complete totality, right? The floor surface regularity should be chosen based on the material movement that you have in the floor. It is very important to understand what materials and how they are going to move around and decide a surface regularity based on this. When testing is done, you have to capture it in full completion, and it is most easy for you to build according to your actual usage rather than coming back after the construction is done and having to correct it according to your usage. So it's much more complicated and difficult to correct it rather than to build it seamlessly when you are actually constructing it. The specification of different aspects has to be captured in the documentation. Documentation is very important at each step, so that if there is a problem, touch wood, you can come back and refer to what went wrong while the process of construction was happening, rather than at the end of it scratching our head and starting a blame game. Quality management approach using a process control is a much better way than to have just a product kind of an approach where you're just testing at the end of it. Now on to Ramesh to start question answer session for the entire webinar today. Thank you for being a very patient audience. I would also like to take one moment to give you a link of the Indian Concrete Institute where you can get your copy of ICI TC9. I remember there were a lot of questions regarding where we can find these guidelines. You can go log on to the Indian Concrete Institute website. That's the link of that is provided in this slide. You can buy, or you can order your copy of the guidelines for yourself. Okay, over to you, Mr. Ramesh.
Thanks, Rama. Quite an energetic session as expected. Rama is always the most energetic guy among the three of us. So I guess we have been able to take a leaf out of all of that. I will allow Rama to take a little bit of a breath while I pose some questions to what I have got from the users. So I have a few questions for Piyush. So Piyush, starting with you, there are some questions that have come for you. So one of the questions came from Parag Panse. Can we avoid subgrade and cast flooring slab directly with some vapor barrier on compacted soil who give good K value and plate load test?
Now, this is actually a very good question. And in my sub-base slide, I mentioned Murum. So Murum is a material that is used as a subgrade as well as a sub-base. So it has those properties. So what is important from a construction point of view, a sub-base should be able to bear construction traffic. And Murum, the right kind of Murum, has that property. So yes, you can avoid sub-base, a separate layer of sub-base, but you need a lot of experience and care. It cannot be done in every situation. It definitely cannot be done for sandy soils. So you need a lot of expertise to be able to do this. The short answer is yes.
Okay, but with a word of caution from Piyush, of course, saying that looking at the conditions that we have, and if you're typically living in Bangalore, you expect a rain any day. So that will not be a right proposition for you to start with, right, Piyush?
I would just like to add.
Cannot be done.
I would just like to add a bit here to what Piyush said. Also refer to the ICI guidelines because it clearly mentions what should be the plasticity index, the liquid limit of the soil, and possibly it would not harm if you already do this test in your soil that you want to fill in, to be able to justify it being used in the as a material for the subbase.
Perfect. Okay. Let's take one more question. It is coming from Arvindan. What is preferred among WBM, WMM, GSB? So what would be the preference?
All right. So typically the sub-base is done in 2 layers. That is typically, I would say, 2 layers of 4 inches of 100 mm. So the first layer you would want to do a WBM or a GSB. So typically what matters is the size of the stone. So in the first layer, you want to have a bigger size stone. WMM or wet mix macadam is also available in different sizes. So what is important is the size of the stone, because in different parts of the countries, these materials are known by different names. So a short answer would be your first layer, use a bigger stone. And in the second layer, use a smaller stone. The reason is you'll be able to finish the surface nicely. You will be able to cut and fill it easily and close the surface. And obviously, you should be sticking to one of the 6 gradations that are specified in the guideline TC09.
Perfect, perfect. One question for you, Navneet. This came from Bhalu Prasad. For corner cracking, when I'm working in Saudi, we used to do slab thickening at all corners. Also, there was two more questions related to the same thing, which came one from Krishna Reddy. Why can't we use increased thickness at corners and have thinner slab in the middle portion, duly making separations in the subbase? Also, another question came from Abhijit. Sir, in most of the cases, due to corner loading, only slab thickness is increasing. What are the possible solutions? So, Navneet, you could take this.
Yeah. So the problem with corner thickening is that you end up, it works like a sunken teeth inside the grade slab. It actually becomes a point of restraint, and grade slabs, they all shrink. And normally it is seen is that at the haunches, you see some cracking, because that's the point where you have the change of the shape. So it has been our experience that although it would be the most efficient way to design, but constructability is an issue, and especially when you want to pour large areas in one go, and you can't really provide for these variations in the sub bases, because mind you, this is also true at the intersection of the joints. So you can't do it always, and if your joints at every 4 or 6 meters, this is certainly impractical. So of course, then the design would be governed by that. So what you could do as a user or a designer is two things. You could possibly ensure that the corner loading does not happen, or it happens at a distance away from the joint, and plan the joint spacing accordingly. Or you could increase the base plate size or the impact
Navneet,
size.
are you unmuted?
I am unmuted,
Navneet, are
yes.
you unmuted?
Yeah,
Okay,
absolutely.
all right, sorry. Okay.
I am not audible. I
No,
don't
there
know.
was some comments. Sorry. Yeah. Okay, please go on. Sorry.
Yes. So or you, second thing is, you could increase the base plate size, so the area of influence becomes higher, and you are able to manage the design properly. So these are the practical ways in which you can get around it. But certainly, edge thickening as well as corner thickening is impractical, and it is also a bit risky, because it causes shrinkage cracks actually.
Okay, thanks, Navneet. I guess all of you are able to hear us well, because I'm getting a lot of comments saying that we are not able to hear you. Uh, for the benefit of everybody else, we will go ahead with the questions. So one more question coming to you, Piyush. These are multiple questions of the same thing, asking about water cement ratio. So Vikas, Kirtani, Kedar Fadnes, Subhash Naik, all are asking, saying, why so high water cement ratio if you're not going to dewater?
Okay, so this question needs some deliberation. I get this is the first challenge for me dealing with the RNC suppliers or the client. They get very uncomfortable when I talk about higher slump or higher water cement ratio. There are two things I stress them enough in my presentation, but I would like to reiterate here. First thing is we need the concrete to bleed. For that, you obviously need water. We need it to bleed for two reasons. First, we want to prevent plastic shrinkage cracks. Second, the hardener needs water to bond to wet, because we want to avoid spraying water on hardener to the minimum. I want to keep it to the minimum. Second thing, we need to understand that typically in Indian conditions, there's a 4 to 5 hour lag between the time you place the concrete and you start finishing. And the kind of weather conditions we have, there's a lot of water that actually evaporates in those 4 to 5 hours, which none of us ever think about. And actually, if we'll be happy to share the graph, the nomograph, that established a relationship between the wind speed, air temperature, concrete temperature, and humidity. And you can do your own calculations. You would realize that a 0.5 water cement ratio actually ends up being a 0.4 by the time you start finishing, and we still need water for the hardener. And even if the water cement ratio is 0.5, the mix is designed to give you an M30. And typically, we don't go above M30. We might go to M35 in certain situations. So, site after site, project after project, we have been able to balance our own requirement from finishability point of view as well as the strength requirement. But yes, this is a big mental block. Why people associate slump with high water, people associate high water cement ratio with lower strength. But what I'm trying to say is we can do the right design by considering all these factors, taking into account both strength and the practical aspects. I hope I've been able to do justice to this question. Navneet,
Yeah.
anything do you want to add? This is an important point.
No, this is okay. Perfect.
Okay, one question to you, Navneet. This is on expansion joints. I think it's one of the favorite topic while we were discussing on the TC09 also, saying, can you please suggest some detailing on expansion joints? So, and there are a lot of questions around the expansion joint itself,
Right.
saying, should we not have, how big, how
Correct.
small? So I guess we could talk about that.
Yeah. So one of the things which is also, I think, essentially given in the guideline as well is uh, the need for expansion joint. Do we really need it? The fact is, for a typical industrial floor, you do not need expansion joints, especially in a country like ours, where any shrinkage in concrete is going to overcome any future expansion that you are going to foresee. So this is typically seen in our sites, also validated over the last 40, 50 years, that the expansion pads lose contact from either edges of the concrete and the pad simply hangs in the middle. And it's a common practice that we provide something like 15 to 20 of expansion pad, and at the end of let's say 9 or 10 months of the project, that gap becomes something like 30, 35 and the expansion pad is simply hanging, and that becomes a point where the joint edges start breaking when you have forklift movement or anything like that. So it's a recipe for disaster. Even where is this concept of expansion joint coming from? If you see, it is coming from highways. It is coming from IRC, and it was coming basically even from 1950, 1960s. The UK theories that base theories that we had adopted for the road pavement design. Now even IRC is essentially, if you look at the latest version, says expansion joints are not needed in typical jointed pavement, except for, let's say, where you have bridge abutment and a road intersection coming in and so on. Other than that, you don't need expansion joints for even roads as per the latest version of IRC. So I think we can stop hanging on to our these I think historical practices and really see that if you remove expansion joints from your industrial floors, especially internal industrial floors, it would do a lot good and improve the overall performance of the floor without really causing any other trouble.
Right, Navneet. Thank you. One question to you, Piyush. I
I
guess.
would like to add one point. Sorry, Ramesh. I would like to add one point. Because the volume of concrete in comparison to the surface area of concrete when it comes to a floor is very different from any other element in your building. So it's very important to understand this difference. And from a material point of view, concrete shrinks a lot more in a floor than in any other element. So an expansion joint is not relevant to industrial floor, that to slab on grade. So yeah.
See, I would also just like to point out here, we are trying to do justice in these 3 hours to different topics. Joint itself is a very big topic. Possibly we can take it up sometime in a later webinar. Possibly, I don't know.
Yeah.
We'll look
Yeah.
into it, but it's certainly a fascinating topic.
Yeah,
Yeah.
certainly,
Sure.
certainly one that took a lot of our discussions. So
Exactly.
I'm sure we'll have more around that. Okay, one question to you, Piyush. This is regarding the current problem that we face everywhere. Typically on river sand. River sand is a problem these days. Can we use engineered sand, M sand, all that, or is the concrete available in India is of international standard or not? This came from Yogesh and Mithal Bhagat. So, do you want to take that?
Yeah. Yeah, yeah. First, I would like to regarding the sand, yes, I agree. There is a paucity of river sand. We use engineered sand in a lot of our projects. There are certain things that you need to take care when you're dealing with engineered sand. They tend to be finer, and they tend to, as a result, and also independently, they tend to absorb more water. So your mix design needs to take care of these two factors, because if you don't do your water correction properly, you can end up with slump loss after unloading the concrete at site. And the other thing would be, you need to be more aware of shrinkage, because the more fine contents in your concrete, the more shrinkage there can be. So you might need to play with the rheology of concrete a bit. So yes, it can be done. It has to be done because our choices are limited as far as sand is concerned. Now coming to the quality of concrete, uh, our country has a lot of variability in terms of material. Internationally, you can expect some standardization of aggregates or cement, but uh, as a company working across the country, we see lots of different kinds of concrete, and I think credit should be given to concrete engineers in general. And I'm speaking for all the flooring fraternity here, to being able to deal with these situations, because trust me, it is not easy. We would want to have the kind of consistency you get in a country like Canada and US. We don't have that, but we are actually still able to deliver genuine international quality flows. And I'm speaking for my fraternity as a whole and not for my own self. So yes, there is a lot of work that needs to be done as far as concrete is concerned. Supply is a big bottleneck internationally. They easily get about 60 to 80 cubic meters an hour, and at our sites, we are very happy if we are able to get 20 to 24 cubic meters an hour. So we are talking an average supply rate in India of about 15 to 18 cubic meters per hour, compared to international supply rate of about 60 to 80 cubic meters per hour, with lots of quality challenges. But we are dealing with it in our own ways. And webinars like these definitely help spread the word. That is why I get a lot of, I'm seeing comments, I'm getting a lot of reactions on water cement ratio, why we need so much water. This is one way of insurance also, that something does not get really out of control at site. Slump is our it gives me as a contractor some buffer to deal with uh, the truck not arriving on time, to deal with cold joints. It just gives me that extra buffer. And I'm not saying increasing slump by adding water. I'm again talking about balancing water as well as admixture. Thank you.
Right. That's good. So let's hope and wish and pray that we'll have concrete industry but takes leaps and bounds, and we are able to reach that level that we are talking about in the developed worlds. One question for you, Navneet, and this came from multiple people. I have noted down from Mr. Kedar Patnis, who's talked about it. But I guess a lot of other people also spoke about the same thing, saying when we cut the slab one third the depth, are we not cutting the top reinforcement in that case?
Actually, you would not be cutting the reinforcement because that would be atrocious. You would provide the top cover in such a way that you have that possibility. So the top cover is always 1/4 to 1/3. So the cut would always be above that. So you would not be cutting through the reinforcement. You will just shift the
Okay,
reinforcement down below the cut.
perfect, perfect.
Typically for
That is
RCC, 1/4 depth is enough, and then you can provide that top cover.
absolutely, absolutely perfect. Okay, second one is, if you look at um, uh, what is the difference between an industrial floor slab and a normal building roof slab? So that is one more question that came up. This came from Yogesh VK. So would I want to elaborate a little more on that, Navneet?
Yeah, so basically, a building slab is a suspended slab which has beams, columns, all these elements which are essentially pin supports, and you have higher bending moments in those elements. But and as Piyush already mentioned, I also mentioned in my presentation, a grade slab or an industrial slab is resting on soil, a sort of set of springs. But that is the main part in terms of difference of performance, structural performance. But also there is a factor that one must note: for industrial slabs, the loads are quite heavy. So the nature of loading, the machines, equipment moving on it is quite heavy compared to what you get in suspended slabs. So please don't be fooled by comparison ki I could give 150 thick roof slab, I can give same 150 thick grade slab. Not really, because it depends a lot on the magnitude of loads.
Okay. Another question that is coming to you only, Navneet, is can we replace steel reinforcement with steel fibers completely in tension zone?
Again, it depends on the application, type of application. I would not be suggesting this for suspended slabs because you don't have sufficient, how do you call it, load redundancy in the system. So we structural engineers like to call a term called degree of static indeterminacy, which is essentially telling a user whether my element has sufficient possibility of redistribution of stresses. So that is not the case there, but for grade slabs, certainly yes, because you have a soil supported system, which is highly indeterminate, and there you have the possibility of road distribution also. So there, definitely, in the tension zone, 100% replacement of steel is possible. It is possible to partially replace rebars in suspended slabs also with fibers, because fibers do act in tension and they under the neutral axis, they are involved in the tension side of concrete. So which is possible, but then I would not say 100% replacement, but partial replacement is possible even in suspended slabs.
Okay. One question for you, Piyush. Um, Again, this is something that is similar to what Rama was answering. So one more question for Rama now. So Rama, you ready to take some questions now?
Yeah, sure. I'm ready. I'm ready.
Okay.
Very much.
Okay. So there one question came from
Right.
Samashiva Raju, which said, "What are the typical design parameters for floor of a speculative warehouse?" Oh, it's an interesting question.
Yeah. Yeah. So many times, I think what Mr. Raju is talking about is many times when we build a warehouse, we don't know what kind of racking or what kind of loads or what is going to be there when the floor is going to be occupied. So when it comes to a speculative warehouse, I would like to take this question in two sections. One is, of course, the load or the structural design of the floor itself. When it comes to structural design of the floor, you will need to speculate the maximum height of rack, depending on height of the building or depending on what kind of tenant you're expecting. If you're expecting a steel component, then you can expect very heavy loads from each of these pallets. If you have, say, for example, an e-retail, you can have a lighter pallet load. So depending on what who is your prospective occupant and the height of rack, you can design the point load that you would expect from that floor that you are building speculatively with not complete detail. That's one. Second, again, will relate to the height of rack that's possible, which is related to surface regularity. If you don't know anything, Tier 34 says build FM2. So which is a reasonable, neither here nor there specification where it's not too tall. So you expect your floors to be somewhere between 8 meter and 13 meter in terms of rack height. So it would work. FM2 would work if you don't have a clear idea of who is going to occupy and what is the height of building. But if you know the height of the building and height of the rack, you should choose a surface regularity depending on height of the rack. That is very important. So these are two aspects I think you should consider when it comes to speculative buildings. Yeah.
Okay. Perfect. So one more question you're coming your way, which is Gopinath is asking, saying, how do you check the floor capacity of an existing floor, which only has drawing details of thickness and reinforcement?
Okay, this is very tricky. Any method or any equipment that is used to do an actual field test of load capacity is not very practical. It's not very easy, and it's not even possible to a complete level. So the best way is to look at the design or the drawings, or if you don't have design and drawings, have cores extracted to see what kind of concrete strengths are there and what kind of reinforcement is there in terms of thickness, the spacing of reinforcement, what is the quality or the status of the reinforcement, how much they've eroded and all that, corroded and all that. So if you do that, you will be able to analytically estimate the capacity of floor. But the actual field test of loads on a full scale floor is not very practical, or it's not even possible many times.
Right, right. Okay, Piyush, one question more on practicality, saying after pouring hardener, people at site will pour water for better power travel movement. Is that good to do?
So again, so it is important. It is best to avoid it, but practically you have to do some amount of it, because if the concrete does not give you enough bleed water, you have no other choice. Because if you do not spray that additional water, that hardener is definitely going to delaminate pretty quickly. Maybe even before the guys have left the site. So the thing to understand is the hardener needs to be wetted either externally or by the concrete. We want to avoid external watering. That is why I've been stressing so much on enough bleed water in concrete to make this happen organically.
So the short answer is, if you want to avoid it, have enough bleed water in the initial design itself, so that you don't encounter such issues.
And everybody does spray a little bit of it, and it is fine.
It's fine. All right, great. Okay. One more question for Piyush. You could take this. How much jointless area can be cast in a day?
So
how much of a jointless floor can be cast in a day?
So a short answer would be, I would say 600 square meters, and the reason is not the limitation or the ability of the flooring contractor, but the limitation on the supply of concrete. We want to limit pouring to about 5 hours, and on an average of about 15 cubic meters an hour, we are looking at about 75 cubic meters. 6-inch slab, that is 600 square meters, is about 90 cubic meters. The thumb rule would be, that is at least what we use, is 100 cubic meters per day is kind of the upper limit. So whatever is the thickness, you can just back calculate using 100 cubic meters per day as a thumb rule.
Okay. And it is most to do with making concrete availability than finishing per se, right? So it is more of the situation on ground that drives it, right?
Correct.
Okay.
The supply bottlenecks, yes.
Supply bottlenecks are the biggest challenge. Great. Okay. So Rama, if you are there, we have one last question. Okay, most flooring consultants use only the flatness survey readings and report the floor to pass the floor as compliant. Is this correct? Is it not correct?
So as I discussed during my presentation also, flatness and levelness are two different properties, and if you have to qualify a floor to conform to a certain surface regularity performance parameter, you will have to be elaborate or complete to cover both these aspects. So levelness is typically measured by an optical method, and flatness is measured by using a profilograph. The only way, if I have to certify a floor for, say, FM2, so only way to test it is, only acceptable way to test it is to test it for levelness using optical measurement, and flatness using a profilograph, and report both of these and then qualify whether a floor is conforming or not. If someone is measuring one and not measuring the other, it's not complete. Somebody cannot certify a floor FM2, say for example, if they are testing only one property. So the answer to this question is, you cannot measure one in place of the other.
Perfect.
And you should, and the client who is specifying FM2 should ask for both. That's the way it should be.
Okay. Yeah. You have one last slide where a lot of people have been asking, saying, can we get a copy of the webinar that we just had? We have recorded it. It will be available, so you can just put across that next slide, where you can, this is for the benefit of everybody, that you could go there, have a look at the webinar. We have recorded the session, and it will be made available to all of you. So this is, you can take note of these details, because this is an input that came from a lot of you guys, saying wherever parts which we were not able to connect, can we have a relook at it? So you could follow us on each of these areas. If you have any questions, please make a note of the email ID and send us your queries, questions. We will try to the best of our ability to be able to answer your questions. We are on this three different portals. So we have on Twitter, YouTube, and you can go to the YouTube channel there, and the recorded version would be available. Right, Rama?
Yeah, we are working on it, and we will also work out a time when this whole session can be replayed. So someone who has missed it, or someone who wants to listen, to this, they can go through a complete replay of the entire event, entire webinar on this link. We are working on it. We'll get back to you. We'll post on one of these forums. And also, after we end this presentation, there is a link that will automatically take you to a slide, a page where you will need to give. It is. We like to receive your feedback. It would be great if you can leave a feedback, suggestion, and everything.
We had close to 1,200 people attending this session, so a good feedback always helps us develop more webinars like this, and come in front of you and present the case study. All right. So it is 1:31. So we are just over by a minute. I don't want to take any more time of yours. Thank you for your patient hearing. It has been wonderful to have you guys on this. And thanks Piyush, thanks Rama, thanks Navneet. You've been given us great information. I'd like to suggested, please go back to IRC portal. Please download the document. It is a very good elaborate document, a very practical one per se. So please take good note of it, and let us all work together to develop the industrial flooring. All right.
Thank you very much, Ramesh. You've been a great host, and we enjoyed every bit of it. Thank you very much, everyone. And once we end this session, this is being redirected. All your webinar pages will be redirected to a feedback form. So please take your time to send us your feedback. Looking forward to see you soon on a next event like this. Thank you very much, all of you, and have a great, wonderful day, and stay safe.
Thank you. Thanks a lot. Thanks a lot.
Thank you, guys. Thank you, everybody. Thanks for.
Thanks everyone.